Have you ever wondered how when you upload a picture to Facebook, it can find people's faces and even suggest who it may be? Or how Google Maps can predict the fastest route based on traffic? If you answered yes to either of those questions, then this is the right course for you. In this course, I'm going to distill many of the complexities of machine learning into a handful of key foundational concepts that you can build upon. The amount of data generated by machines and humans is mind-boggling, and it's growing faster than it ever has. According to IBM, 90% of the data ever created was created in the last 2 years. Imagine all the power that exists in that data if we could just harness it and use it in the right way. The challenge is that a lot of this data is completely unstructured and really messy. Or maybe there's simply too much data to even know how to extract value out of it. This course will give you the toolkit needed to wrangle unwieldy data and translate it into a form that could be used to generate some incredibly powerful insights by way of machine learning. More specifically, this course will cover some of the foundations of machine learning like exploratory data analysis, cleaning your data, fitting robust models, tuning hyperparameters, and finally, evaluating a model to ensure that it generalizes to unseen examples. Once you finish this course, you'll have all the tools to harness unstructured data of all types to go from that messy data to concise and accurate predictions from a machine learning model. This will allow you to deliver powerful solutions to complex business problems. Before we get started, I want to go over some assumptions about the background knowledge that will help you get the most out of this course, as well as some other concepts that would be helpful but not necessarily required. First, it'll be helpful if you have some working knowledge with Python. There won't be anything too complex, but I won't be covering the most basic concepts. So it'll be helpful if you broadly understand how it works and some of the basic syntax. Beyond that, it would be helpful if you have some experience with the NumPy, Pandas, and scikit-learn libraries, as we'll be relying on each of those fairly heavily throughout this course. Now, if you have some experience with statistics, that will be helpful, but it's not absolutely necessary. Some experience handling data and doing some basic data analysis or data manipulation would also be helpful, but again, not required. Lastly, having some familiarity with some of the key concepts in machine learning will be helpful as well. If you don't have any experience with machine learning, don't worry, we will be covering the basics so you won't be left behind. Before diving into the course, we want to make sure that you're set up with the tools and the software you need to follow along. I'll be working with Python 3.7. It's important to note that if you're still running Python 2.7, some of this code may not work correctly. I'll also be running the code within Jupyter Notebooks. Jupyter Notebooks is a fantastic tool that allows you to combine live code, explanatory text, visualizations, and equations all in one concise package. Luckily, everything you need for this course, that's Python 3.7, Jupyter Notebooks, and all the packages you'll need, can be acquired very easily by installing the free Anaconda 3 distribution. This lesson is going to focus on the seemingly elementary question, what is machine learning? We're starting here just to make sure we're going into the rest of the chapters with the same understanding. If you ask 10 data scientists to define machine learning, you might get 10 different answers, but they will revolve around some key themes. So let's explore a few of those definitions. The first definition comes from Arthur Samuel. Samuel is recognized as one of the first real machine learning pioneers, and he was actually the first to coin the term machine learning. He defined machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. This is a pretty good definition, but it's a bit vague and seemingly magical. So let's try to get a little more concrete. This definition from the University of Washington hits on one key concept that is missing from the previous definition. Machine learning algorithms can figure out how to perform important tasks by generalizing from examples. Again, generalizing from examples. That's a very important point that I'll revisit in just a minute. So borrowing that portion from this definition, here's my aggregation of several definitions that I think makes things just a little bit more concrete. Machine learning is fitting a function to examples and using that function to generalize and make predictions about new examples. This hits on the fact that the algorithm or machine learning model is based on the data that you feed it, that's learning from examples, and that the entire goal is to use that learned model to make predictions about new examples. As I mentioned before, this is a really key concept. In other words, machine learning models learn from trends in past data to make predictions about future data. If you think about it, we all do this on a day-to-day basis. We learn from our past experiences to adjust our behavior or our views in the future. With that definition in mind, an even simpler definition of machine learning is simply pattern matching. Again, a model learns from a pattern in data that was fed to it, fits a function to that pattern, and then uses that function to pick up on those patterns in future data to make predictions about it. Let's look at a really simple example of machine learning. So this is a very simple single variable linear regression. So this plot is showing the number of umbrellas sold based on the amount of rainfall. So the model seeks to predict how many umbrellas will be sold based on the amount of rainfall. The model in this image is just represented by this red best fit line. You might remember that the equation for a line is just y equals mx plus b, where y is the thing that you're trying to predict, which is umbrellas sold in this case. X is the thing that you're trying to use to predict it, that's rainfall in this case. M is the slope of your line, and b is the y-intercept. So this best fit line on this plot has an actual equation. The equation of that line is your model, or it's the function that is fit to this data. Remember back to our definition. Fit a function to examples and use that function to generalize and make predictions about new examples. So we covered that first part. We have a function or a model that is fit to data, that's this line. Now, what does this model allow us to do or say? Well, if it happens to rain 110 millimeters, even though I don't have any examples of days where it rained exactly 110 millimeters, I can say that based on my model, we could expect about 30 umbrellas to be sold. So this is a very simple example of a machine learning model. Now that we're on the same page of how we're defining or thinking about machine learning, let's pivot towards something a little more practical. Let's talk about the types of problems that machine learning might be able to help you solve. To make this broad enough to apply to any problem that you might have, we're going to walk through some questions that you should be asking to see if this is a problem that you could use machine learning to solve. From a high level, when presented with some kind of problem that you'd like to solve, there are two primary questions that need to be addressed. The more general question, is this a type of problem that can be solved using machine learning? And then more specifically, is this particular problem one that can be solved with machine learning? To clarify, your problem could be one that in general terms can be solved using machine learning, but you might be lacking some of the specific aspects required for machine learning. So let's jump into some more detailed questions that we should be asking. So focusing on that first question, when we talk about the type of problem that can be solved, what are we really talking about? So one question that we should be asking is, does this problem require a prediction or some type of bucketing into categories? Generally speaking, if there's no prediction or segmentation to be made, then machine learning is not needed. And then secondly, is the problem relatively self-contained? If there are too many additional or outside factors, there will be too much noise for a model to actually make an accurate prediction about whatever you're interested in. For instance, if you're determining whether a given transaction is fraudulent, that's a very hard problem, but it's relatively self-contained. You can extract what you need to make a prediction from the transaction itself and the past transaction of that card owner. However, if you're determining whether a credit card company is going to succeed or fail, that's something that's a little too difficult for a model to determine because there are too many additional factors, both internal and external. Now, if you've answered yes to the previous questions, and this is a type of problem that can be solved with machine learning, now we need to assess whether the particular problem that you have can be solved with machine learning. In other words, do you have all the components needed to build a model? So some of the key questions that you need to answer is, first, do I have data with labels? You need to teach the model what certain behavior looks like. If you don't have labels for your examples, the model can't learn from that past data. Secondly, do I have the ability to assess the quality of the model? Even if you have labels, it can still be relatively complex to determine the accuracy of the model. And then lastly, do I know what an acceptable accuracy threshold looks like? So if you're applying this at work, there's usually some cost to deploying a model. You should be able to tie the model performance to the cost or savings of some sort. So in other words, do I understand the business impact of this model? What is the break-even point? What would even be considered a success? So these are just some of the questions that you would ask yourself when determining whether this problem is a fit for a solution using machine learning. Now let's try and reorganize all this information into a flowchart that should hopefully provide a step-by-step process of the questions to ask to determine whether your given project proposal is a fit for machine learning. So again, you start with a project proposal. The first question right off the bat you should ask is, does this require a prediction or bucketing? If the answer is no, then you need to look at other solutions. If the answer is yes, then you can move on and say, is the problem relatively self-contained? Are there too many outside factors? If the answer is no, then revisit the approach to the problem. You probably don't want to use machine learning. If the answer is yes, then you can start looking at the actual data. And this is where we get into, is machine learning a fit for my specific problem? So do I have data with labels? Maybe the answer is no, but you can get labels. If you can get labels, then you can move on to the next question. Do I have the ability to assess the quality of the model? Do I have some metric that I'm trying to optimize? If the answer is yes, then you move to the step of tying this to the business impact. Can I determine an acceptable accuracy threshold? This is where we're tying it to the business outcome. What is the break-even point? What type of accuracy do I need to get to achieve the business objective? If you can answer yes to all of those questions, then you're looking at a problem that's a really good fit for machine learning. And then lastly, some examples of machine learning in everyday life would be spam detection in email, speech recognition in Siri or Google Home, recommendations from Netflix, Spotify, and lastly, fraud detection. In this lesson, we're going to discuss why Python is being used in this course, and more broadly, why Python is the most popular language for machine learning. From a very high level, Python is used for machine learning for a few reasons. One, it's very popular right now and has a very large user base. More importantly, that large user base means nice documentation, lots of quality tutorials, and a lot of activity on Stack Overflow. Secondly, Python has more machine learning packages than any other language. And lastly, Python is fairly easy to learn, and it's remarkably easy to work with, especially in those machine learning packages. The barrier to entry is quite low, and we'll see this in just a minute. So digging into each of these points a little bit more, let's take a look at the results of Stack Overflow's yearly developer survey. So this is the results from Stack Overflow's survey, where it's looking at the percent of overall question views each month by language. You can see the massive growth in Python over the last 6 years. And then they take that and they project it out over the next year or two. You can only imagine where it will go beyond that. So to summarize, Python's very popular right now, it has a large user base, and it's also the fastest growing language. More specifically, Python is a very popular tool for machine learning. So this is just looking at the interest over time using Google Trends. And by looking at this blue line, you could see the gap that Python has created over R, Java, Scala, and C since 2015. Python is like a Swiss Army knife when it comes to data. It has very easy to use packages for pretty much anything you'd like to do. Classic machine learning, deep learning, natural language processing, image recognition, data visualization, and data analysis. I could go on and on. There are great packages for nearly anything you want to do in Python. And on the last point that we talked about, Python being very easy to use, particularly for machine learning, let's jump over to some code to walk through that quickly. We're going to use a classic machine learning data set to build a very basic logistic regression model in just a couple lines of code. The goal is just to illustrate how simple it is to build a basic machine learning model with Python. Now, before we dive in, I just need to call out one thing. I love scikit-learn for so many reasons. One thing I don't necessarily love is that scikit-learn pushes out a lot of future warnings, meaning that every time you run a method with changes coming in an upcoming version of scikit-learn, they will print it out as part of the return. This is nice for keeping tabs on upcoming changes, but often it can be a bit overwhelming. So for this course, I'm going to silence them using the warnings package. And we'll just tell it to ignore all warnings that fall under the future warning class. So the way we do that is we call future warnings, we call the filter warnings method from within that module, we tell it we want to ignore, and what we want to ignore, we pass in category equal to future warning. So any warning outside of that class will still be printed out. It's just this specific class of warnings that will be silenced. It'll just help us clean up our printouts. So we're going to run that. So we'll also be importing the data set and the model from scikit-learn. So let's go ahead and run that. And then lastly, we call this load iris method that will load the data set that we're going to use for this example. So now we just want to call the logistic regression object. And then we'll just call the .fit method that is contained within this logistic regression object. And then we just need to pass in iris bracket data. And that's the training data that we want to use. And then we'll pass in as the second argument, iris bracket target. Right? So that's going to be our target variable or the labels that the model is going to learn from. And don't worry about understanding this stuff right now. This is what we're going to dive into. So then we'll just run that. And now basically what we have is we have a fit model stored as model. Now this is something that we can actually make predictions with. So let's go ahead and do that. So we'll just call model.predict. And we'll pass in iris again with data, and that will take that stored model and we'll make predictions. So now we can just run this, and what it's going to do is use that stored model and make predictions using the features. So now we fit a model in one line. I just want to emphasize that this is for illustration purposes only. I broke a number of rules here, but I just wanted to show how simple scikit-learn makes it to fit a model in Python. And the great thing about scikit-learn is every algorithm follows this API that you saw, where you're calling .fit to build your model or fit your model, and then .predict to make predictions using that stored model. Now at this point, you may be asking yourself, if we can just fit a model with one line, why do I need to take this course? Now, I illustrated that you can fit a model in one line, but it doesn't mean it's a good model. Recall our discussion in the last lesson. There's an accuracy threshold for any given model. In business, if you fit a model like I did here without really exploring the data or examining different hyperparameter settings or really evaluating our model in every way, you could cost your company thousands or potentially even millions of dollars. Fitting a model is the easy part. No expertise is needed there. Anybody can really do that. Fitting a quality, robust model that will make accurate predictions on data that you can actually tie that to the business impact. That is the tricky part, and that's what this course is going to give you the tools to do. In this lesson, we're going to try to develop an understanding of how the fields of machine learning, deep learning, and artificial intelligence are related. These terms are wrongfully used interchangeably. As we work through clarifying what machine learning is, I also want to be clear about what it is not. Just doing a simple Google search of these terms will return hundreds of Venn diagrams attempting to describe how these three terms are related. Here's one such example, and I only show this just to illustrate how difficult it is to understand some of these diagrams. There's just way too much going on here to really understand the certain relationships that we're interested in. What I'm hoping to lay out in the coming slides is a much more simplified explanation of how these terms are related. So beginning with machine learning, this is the definition that we saw back in lesson 1. Machine learning is the process of fitting functions to examples and then using that function to generalize and make predictions about new examples. And then we also discussed a simpler related definition that is just pattern matching. So a model will basically learn a pattern from past examples, and then it will fit a function to it, and then it'll use that function to pick up on similar patterns in future data to make a prediction about it. So let this circle on the right-hand side represent all things machine learning. Now, deep learning. Deep learning resides entirely within machine learning. That is, It's a subset of machine learning. The definition of deep learning is very similar to the definition of machine learning. It is still fitting a function to examples, but the difference comes in the fact that these functions are then organized as connected layers of nodes. In other words, you'll have many functions connected together in one network where each function is responsible for a very specific thing. This is still all with the goal to generalize and make predictions about new examples using our network of functions. An alternative definition is just more sophisticated, connected pattern matching. So again, instead of just using one function to match a pattern, you're just using many functions to match a pattern. Now, this may seem very vague, and that's quite okay. Deep learning is not the focus of this course. The one important thing to take away is just that deep learning is a type of machine learning. It is a subset of machine learning. There are things that are machine learning that are not deep learning, but there's nothing that is deep learning that is not machine learning. Now, the last layer that we're going to add on top is artificial intelligence. Artificial intelligence is a superset of machine learning and deep learning. In defining it, we're going to split it into two separate definitions: weak AI and strong AI. Weak AI is intelligence specifically designed to focus on a very narrow task. The key takeaway here is that weak AI is machine learning, intelligence designed to focus on a very narrow task, like identifying fraudulent credit card charges. But then you're not going to take that model that was built to detect fraudulent credit card charges and recommend Netflix movies to you. Strong or general AI is a machine with consciousness, sentience, and a mind. General intelligence is capable of any and all cognitive functions and reasoning that a human is capable of. So general AI is a superset of many things. Only one of those things happens to be machine learning. But there are many things under the umbrella of AI that is not machine learning. So this is just a high-level overview of how these three terms are related. Deep learning is a subset of machine learning, which is a subset of general artificial intelligence. These should not necessarily be used interchangeably without specifying what type of AI we're talking about. In Lesson 2, we discussed some common problems that machine learning can help you solve. In this lesson, we're going to run through some real examples of machine learning in our everyday lives. The first example is personal assistants, whether it's Siri, Google Home, or Amazon Echo. All of this speech recognition software is built using machine learning. This small diagram illustrates how Siri takes what it thinks it hears, runs it through a model to find out what was likely said, and then executes some query to return a response. More specifically, the part where it takes what it thinks it hears, maybe bet a timer, and smooths that out into the most likely thing the person actually said, so maybe that's set a timer, is the core of the machine learning functionality here. The next example is recommendation systems, and we're literally surrounded by these, from shopping on Amazon to Netflix to Facebook friend recommendations to Twitter. All of these recommendation systems are driven by machine learning. This is a very simple example of one method called collaborative filtering. Collaborative filtering uses similarities between users to make recommendations. So in this example, both Bob and Tom have bought and enjoyed pizza and salad. Based on their purchase and rating history, we know that Bob and Tom have similar taste. Bob has also bought and enjoyed soda, but Tom hasn't, so the system should recommend soda to Tom. So that's the 10,000-foot view of how collaborative filtering works. Another example of machine learning is with ride sharing like Uber or Lyft. There are a number of ways in which machine learning can be used. From route efficiency based on traffic to driver-rider pairings based on rider location and driver location and maybe traffic, to determining efficient ways to pair two riders together for Uber Pool, and then even optimal pricing based on demand of users and supply of drivers to keep the appropriate balance. Uber has made all of their traffic data publicly available and has built this really neat tool called Uber Movement to show how long it would take to get to different areas of a number of different cities, given time of day, day of week, and things like that. So the colors correspond to travel times, and you can click around to see how long it takes to get to different areas outside of downtown LA. Lastly, one of the newest and most popular areas of research and implementation is in self-driving cars. And this is using deep learning, which remember is just a subset of machine learning. Think about everything that goes through your mind when you're driving a car, most of which comes instinctively once you've been driving for a couple years. So that might be driving the speed limit, tracking all the cars around you, making sure you're not tailgating, and watching for brake lights. You effectively need a deep learning network to learn all of these patterns that our brain has learned over years of driving. Now that we've set the stage of what machine learning is, what it is not, and we've discussed a few examples of what machine learning looks like in everyday life, let's talk about some common challenges we run into with machine learning before we start diving into code in the next chapter. Let's first take a quick look at this slide that we saw back in Lesson 2, where we talked about questions you should ask to determine if machine learning is a reasonable choice to solve your given problem. I bring this up because common challenges in machine learning flows pretty directly from these questions. So in thinking about common challenges we run into with machine learning, they tend to fall into 4 high-level categories: problem scoping, data, infrastructure, and latency. We'll walk through these high-level groups one by one, and I should clarify that these aren't necessarily blockers so much as they are just simply things to look out for when you're trying to solve a problem using machine learning. We can run into issues if we're not actually solving the right problem, and this might seem really trivial, but being able to translate an actual business problem into data and then into a model that will actually solve that exact problem isn't always as easy as it would seem. And then secondly, maybe the tolerance threshold is undetermined. So recall we talked about this back in Lesson 2. If you don't quite understand the impact on the business, then you can't translate it into what an acceptable level of accuracy is for the model. So maybe your break-even point where you start to achieve the desired business outcome is 70% accuracy. Maybe it's 80%. Maybe it's 98%. This is critical to understand before you can even consider deploying a model. The last problem scoping challenge is that maybe you develop your model in a training environment with static data and you evaluate that model and everything checks out fine. But that data isn't real live data from the environment in which the model will live. Oftentimes, it's a huge challenge to properly gauge the impact a model will have once it actually goes live in a production system. Next up are the challenges related to data. And these are a little bit more straightforward than the problem scoping section. So first, even in the era of big data, it's actually a very common problem to not have enough data. And remember, this is all relative. You need enough data to pick up on the underlying pattern in the data. So if you're trying to predict umbrella sales from rain amount like we saw before, the correlation or the signal is strong, so we need very little data. But trying to do something like predict fraudulent charges on a credit card has a lot more noise in the data and would require much more data for a model to pick up on the underlying pattern in the data. On the other extreme, maybe you have too much data. My favorite definition of big data is that data is big when managing the data becomes part of the actual problem. Another common problem is that data doesn't always have labels. If you don't have labels, the model simply can't learn the pattern that you want it to learn. Sometimes this requires hand labeling, or sometimes you can determine some proxy for the label in an automated way. Lastly, perhaps the data you have access to is of a reasonable size, but it's really biased or dirty or noisy. So you'll have to spend a large chunk of your time cleaning your data. This is a very common problem. The next challenge that we run into is related to infrastructure. Often, when models are used in business, they're plugged into an environment where they're run in real time. Using our fraud detection example, we need this model to be run on every single transaction that comes in the door. Depending on the company, sometimes this falls on the lap of the same person that actually built the model. And it's quite uncommon to have somebody that has the skill to build a quality machine learning model while also having the skills to build out the system to run the model in real time. Particularly in the case when you have true big data, compute power can become a big roadblock. When you have terabytes worth of data to process, you need a lot of compute power, and you have to be very careful about how you write your code to make sure it's efficient. And I'm going to lump these last two together. Once a model is built and tested in your training and test environment, you ideally want to test this in the live environment against whatever mechanism is currently governing the process that this will plug into. So in our fraud detection example, perhaps the initial model was some basic decision tree, and now you've built something a little bit more complex to replace it. You would want to do some sort of A/B testing in a live environment to see which model's doing better. The potential consequence is that the new model might be much worse, and that can have a real tangible impact on the company by running it live. Then once that A/B testing stage is passed, you'll want to track the model performance over time to make sure that you're not seeing model degradation. A lot of companies don't have anything in place for this type of tracking. Lastly, that brings us to latency. There are two main challenges here. The first is that a model takes too long to train. This can relate back to having too much data or not having enough compute power for the data you have. If a model takes days to train, then it can be really difficult to iterate and improve. You need to plan your time very carefully when this challenge comes into play. And then lastly, the model might take too long at inference time. Inference time means when the model is deployed and needs to make real-time decisions. So with our fraud detection example, if the model takes even 500 milliseconds to spit out a response every time it's fed a transaction, it's going to get way behind really quickly when it has thousands of transactions coming through per second. In this chapter, we're going to start digging into our data to explore it and clean it. But first, the question of why needs to be answered. And we're going to start by talking about exploratory data analysis, and then we'll discuss data cleaning. So for both of these sections, I'm going to split it into two portions, the why and the what. Then that will set the stage to jump into the data in the next few lessons and see some of these concepts in action. Now, 3 reasons that we do exploratory data analysis, or EDA for short, is to understand the shape of the data, learn which features might be useful, and then we use this information to inform the cleaning that will come next. So you can imagine this stage as building the foundation for the house that you're going to build on top of it. Without a firm handle on what this data looks like, your foundation is going to be shaky, and the house or the model built on top of it will likely end up being suboptimal. Okay, so what do we actually do during this phase? We could easily do an entire course just on this. There's so many different paths to go down depending on your data. So to summarize in just a few quick bullet points, this step includes getting counts or distributions of all your variables to understand the shape, and you do this for both input features and the target variable. And then you could look at the data type for each feature. Is it an integer, string, maybe a Boolean? And then you check for missing data, you understand correlations between your features, and maybe identify duplicates in the data. I did just want to mention that you usually head into EDA with a few key questions that you want to answer, but you often allow the data to take you where you need to go within some constraints. It's important to have structure, but be flexible enough to dig into areas that you hadn't planned on looking at before you actually got your hands on the data. Okay, so moving on to data cleaning. Why do we need to do data cleaning? The overarching point here is that machine learning models are not magic. If they were magic, then this course probably wouldn't exist. Machine learning models are algorithms that respond in a systematic way to the data that you give it. If you give it biased data, you'll get a biased model. If you give it incomplete data, it will return weak predictions. I cannot overstate how important data cleaning is in producing a quality model. It prepares the data in the best way possible to allow the model to pick up on underlying patterns that we want it to fit to. Under that overarching theme, you have shaping the data, you have removing irrelevant rows or columns, and adjusting features to be accessible for the model. We'll see this in action in the rest of this chapter. Largely, data cleaning is completely driven by your exploratory data analysis, but a few things to consider or look for when you're doing this. The first is anonymizing your data. There are heavy regulations on data privacy, so generally you should be removing any personal identifiers from your data if this isn't publicly available data. The next is encoding categorical variables. We'll see a little bit more of this in future lessons in this chapter. Then you might be filling in missing data. And lastly, if you have skewed features or outliers, then you'll want to prune or scale it. So we're going to start with some very basic exploratory data analysis. on just the continuous variables. In this lesson, we'll do some high-level exploration, and then the next lesson, we're going to plot some of the continuous features. So for this entire course, we're going to use the Titanic dataset, which is a publicly available dataset that is very commonly used for machine learning. This dataset contains information about 890 people who were on board the ship when it departed in 1912. Some people aboard the ship were more likely to survive the wreck than others. There were not enough lifeboats for everybody, so certain groups of people were prioritized. Our task is to build a model to predict which people would survive using certain information about the 891 people on board. The features that will be used are as follows. There's a name feature, which is just the name of the passenger. There's a P-class feature, which is the ticket class, so that's first, second, or third. There's a sex feature, and that's the gender of the passenger. There's an age feature, which is just their age in years. Then there's a SIB-SP feature, which is the number of siblings and spouses aboard. Parch feature, which is the number of parents and children aboard. There's a ticket number feature, passenger fare feature, cabin number feature, and then lastly, embarked, which is the port of embarkation, which is just 3 different codes for 3 different cities. So let's start by reading in our data. Now we'll import matplotlib, numpy, pandas, and seaborn, and then we'll tell matplotlib that anything that we plot in the next lesson, we want it to do it right in our notebook. So let's go ahead and read in our data set that we have stored in our directory. And then the first thing that you always want to do is actually look at the data. Now, just by looking at the data, I'll call out 2 things very quickly. The first is that we do have personal information here in the name feature, but this is public information, so that's okay. So with that said, name, passenger ID, and ticket aren't going to be of much use here in determining whether a passenger survived, so we're going to just drop those. In addition to name, passenger ID, and ticket, sex, cabin, and embarked are all non-numeric features, which we'll be exploring later on this chapter, so we're going to drop those fields as well just to keep this exploration a little bit cleaner. So let's go ahead and drop those first. I first defined a list here of all the features that need to be dropped. So that's passenger ID, name, ticket, sex, cabin, and embarked. In order to drop them, we'll call the data frame, which we've named Titanic, call the drop method, pass in that list of categorical features, and then we have to tell it axis equals 1, and that just lets pandas know that we're trying to drop the columns and not the rows. If you do axis equals 0, it will drop the rows. And then lastly, we'll tell it to drop these features in place. In place equals true. In other words, what that tells pandas is we don't want to create a new data frame from this. We just want it to do it right inside of Titanic. And now let's go ahead and print out the first 5 rows by calling .head on the data frame. So now you could see a much cleaner data frame where we only have the continuous features here. So, starting to explore the features, one useful thing to do with numeric features is to call the describe method on your data frame. This will help you get a feel for the shape of your data by printing out the count and some distributional information to start to get a feel for your data. I'll just call out a couple things here. You'll notice under age, the count is only 714, whereas it's 891 for the other 5 features. The reason is there's missing values with age, which we'll dig into in just a few minutes. Another thing to mention is for the survived feature, that's our target variable. That's binary. It's either 0 or 1. And since it's binary, we can use the mean to tell us what % of people survived in this data set. So this is telling us that 38.4% of people in this data set survived. And it's always useful to know that when you're doing a classification problem. And then we can see for the integer variables, that's p-class, sib-sp, and parch, these are all what's called ordinal variables. So these are integers, but there are only specific levels. So for instance, for p-class, that's ticket class, there's only a first class, a second class, and a third class. Now just keep that in the back of your mind for the next lesson, as it's going to differentiate how we explore these different features. The next thing that's useful to know is understand which features might be strong indicators of whether somebody survived or not. One way to do that is to just group by the two levels of survived, so that's 0 and 1, and generate the average value of the other features at those two levels of the target variable. So we do that by just calling the data frame, then we call the group by method on that, and we pass in survive. So that will group our entire data frame into two separate groups, one for everybody who survived and one for everybody who did not. And then what we want to do is we want to call .mean, and what that will do is it'll return the average value for each feature based on whether the person survived or did not survive. So what we're looking at here is, for instance, the average age of a person that didn't survive is 30.6, and the average age for somebody who did survive is 28.3. So which of these features are really standing out? So fare certainly stands out. As you can see, the average fare for somebody who didn't survive is around $22, while the average fare for somebody who did survive is over $48. Class also stands out, and it makes sense that class would be correlated with fare. With that said, this isn't a complete picture. So just keep these things in the back of your mind as we move forward. So speaking of keeping things in the back of your mind, recall that previously we noticed that age had some missing values. Now, whenever you have missing values within a feature, we want to understand whether those values are missing at random, for instance, if it was never reported for certain people, or if it's missing in a systematic way. For instance, they didn't ask the age of anybody in first class, because this will inform how we handle these missing values. So one way to determine whether these are missing at random or not is to do what we did above by group by, but this time we're going to group by whether age is missing or not. So we can just copy this down, and we're going to change what we're grouping by, and we'll call our data frame, and then we'll call just the age feature, and then we can call the isNull method. And what this method will do is it'll just return a true or a false based on whether a given row has a missing value for age or not. And what this isNull method will do is it will just return a true or a false based on whether a given row has a missing value for age. So we'll run that. And one thing that I want to mention is that when it says age is true or false, that means true or false on whether it's missing. So age equals true means that age was missing, and age equals false means it was not missing. We notice that there does seem to be some splitting. People without age reported were less likely to survive, had a higher class number, had fewer parents or children, and a lower fare. So based on all this information, we could theorize that age wasn't recorded for people in the bowels of the ship that maybe were traveling alone. But in summary, nothing really jumps out here that would require us to treat these missing values any specific way. Keep this in mind, though, because you'll see a totally different result for some missing values we find in one of the categorical features. Okay, so now we've done some very high-level exploration of the continuous variables, and we've learned just a little bit about our features, like the fact that age is likely missing at random, and fare and class might be good indicators of whether somebody survived. In this next lesson, we'll dig into plotting our continuous features, which often helps us uncover additional patterns in our data that weren't necessarily visible in this high-level overview. Let's go ahead and pick up where we left off in the last lesson. So in this section, we're going to dive a little bit deeper and plot some of these continuous features. Now, above all, we'd really like to understand the shape of our features and how they relate to the target variable. One of my favorite ways to do that for continuous features is to plot overlaid histograms, where we can compare the distribution of a certain variable, say age, for people that survived versus people that did not. In the last section, we saw that the average age for somebody who survived was 28.3, while the average age for somebody who did not was 30.6. This just adds a little more detail by looking at the actual distribution instead of just the mean. Now remember in the last lesson, we talked about how age and fare were truly continuous variables, while p-class, sib-sp, and parch were ordinal variables. So we're going to focus on age and fare with these overlaid histograms, and then we'll explore a different visualization for the other three features. So this code that you see here, we're going to loop through these two features, and essentially what this code will do is it'll grab non-missing values, and assign them to two lists, and then we'll plot those two lists on an overlaid histogram. So let's go ahead and run that. In the last lesson, we concluded that based on averages, there isn't much difference in age between people that survived and those that did not. This plot more or less confirms that. But it's nice to also see the age of this feature, where we could see there's a heavy concentration of people between 20 and 30, maybe extending out to 40. But the distribution between survived versus not survived is relatively similar except for the very low end. Now let's look at fair. We noticed a fairly drastic difference in the averages. The average is about $48 for those that survived and about $22 for those that did not. Now, this plot highlights the caution that you have to take with looking at only averages instead of full distributions. Anything outside of this very first bar here, you'll see that the likelihood of surviving versus not surviving is actually quite similar. For instance, in the second bucket right here, it looks like maybe around 70 people survived, so that's that green bar, while 100 did not, that's the pink bar. And then it gets closer from there. So the takeaway here is just that FAIR can probably help us predict whether somebody survived, but it's not quite as cut and dry as the averages indicate. The average is likely being impacted by some outliers. Now let's turn our attention to P-class, SIB-SP, and Parch. So the way that we're going to plot this is with what's called a categorical plot, where we can plot the survival rate for each level of these features. So hopefully this will make more sense once we actually plot this. So we'll start by calling the catplot method from within SNS. And SNS is what we stored Seaborn as. So now it expects an X argument. So what is the X axis? And we'll return to that in just a minute. And then what is our Y? So our Y is going to be survived. And then give it the Titanic data set as our data. And the kind of plot we want is point. And you can explore other types of categorical plots in the Seaborn documentation. Now, lastly, aspect is what controls the size. We're just going to pass in 2. And you can explore that as well in the Seaborn documentation. Now, I said that we'll want to return to what we're passing in as X. Like we did before in the previous example, I'm going to create a loop since we want to do the same exact thing for 3 features. So what are those 3 features? Those are going to be P-class, SIB-SP, and Parch. So we create this list, and then we'll say for column in this list, run this Seaborn catplot method. And so for X, what we're going to pass in is COL, and that'll cycle through P-class to SIB-SP to Parch. Now, the problem here is that Seaborn needs to know to create a new plot for each item in the loop. Now, to do that within the loop, we can call PLT, which is matplotlib, figure, but then we need to pass something into that. Now let's go back up to the loop. One trick that we can do is we can call enumerate, and what this will do is it'll return 2 things. It will return the index of the list, and remember, lists start with index 0, so it'll return 0 for P-class, 1 for SIB-SP, and 2 for P-arch. And then it will also return the actual item in the list. So now we've adjusted our for loop to say return I, which is going to be the index of the list, and the actual column name. And then we'll just plug in I into figure, and that will tell it to create a new plot every iteration through the loop. Now we can go ahead and run this. So what are we looking at right here? Well, the point on each of these plots represents the percent of people that survived at each level of the input feature. So for first-class passengers, roughly 63% of those people survived. And then these vertical bars represent the error. So if we have a lot of data for a given level, the vertical bar will be small, indicating that we're quite confident. Now, if we have limited data, the vertical bar will be really large. So we see some obvious trends here. Better class, first class, is more likely to survive than third class. Now, we can see that people with more siblings are also less likely to survive. And lastly, though this relationship is not quite as clean, those with more parents or children are also less likely to survive. Now, it seems like SIB-SP and Parch all have to do with family members aboard. And when you have more, you're less likely to survive. So it seems like perhaps we could merge that into a single feature. So let's go ahead and explore that. So all we have to do is add together this SIB SP feature together with the Parch feature, and then we'll store that as a family count feature. And then we're going to plot it using a categorical plot again. So we can just copy this code right down here, and then we'll just replace the X with family count. And we can leave survived. We're still using a Titanic data set. We still want a point plot, and we can go ahead and run that. So you can see that generally this pattern still persists. As you can see at the lower end, it increases a little bit, but the overall trend here, you could still see that the more people in your family, the less likely you are to survive. It's important to note that if you can combine two features into one while maintaining the same pattern or trend, it's usually a good idea to do so. Just cleans up your data so your model has fewer things to look at. So moving forward, we'll plan to only use this family count feature. Previously, we talked about how exploratory data analysis will inform our data cleaning. In this lesson, we'll take what we learned in the last two lessons and actually implement some of the necessary cleaning. So let's start by importing our data. And then we discussed in the last lesson how passenger ID doesn't really factor into whether somebody survived or not in any way. So we're going to go ahead and drop this feature in place just like we did in the previous section. So we do that by calling the drop feature on the Titanic dataset. We tell it to drop passenger ID. We pass in axis equals 1, and that tells it to drop the column instead of trying to drop rows. And lastly, we'll pass in this in place equals true, which tells pandas to alter the Titanic dataset as it stands now instead of trying to create a new data frame. So we'll run that, and you can see that this passenger ID is no longer in our data frame. Now, in the last lesson, we learned that age has some missing values. We also checked to see if the missing age values were correlated with any other variables to see if it might actually mean something, or maybe it was just missing at random. As a refresher, let's just look at this output of this line of code again, and we'll highlight the fact that there are some differences, but probably not enough to conclude that this isn't just missing at random. So we'll treat it as missing as random, and we'll use one of the most naive but useful methods for filling in missing values. And that's just replacing the missing values with the average value for that feature. That way, it satisfies the model by making sure that there's a value in there, but by replacing it with the average value, it's not biasing the model towards one outcome or another. In other words, because the age value is just its average, it will rely on all of the other features in the model to try to decide whether the given person survived or not. Okay, so the way that we'll fill in these missing values with the average value is we'll call the age feature from the Titanic dataset. We'll use this fillNA method, and all we have to do is tell it what we want to fill all the missing values with. So we want to fill it with the missing value of the age feature. So again, we'll call Titanic and the age feature, and then we'll just call the mean. And that'll just take that entire column. It'll compute what the average value is. So this fillNA method will cycle through all the age values in that column. It'll find where the missing values are, and it'll just fill it with whatever this mean value is. Lastly, we just have to pass in this in place equals true argument, again, just to tell it to alter Titanic as it stands now, rather than creating a new data frame. Okay, and then the last thing we're going to do is we're going to call this Titanic.isNull.sum, and what this is going to do is it's going to tell us where we have missing values across each of the columns. And this is just going to be a check to make sure that this did its job. Let's go ahead and run that. And you can see now for age, it's indicating that there are 0 missing values. So let's just check it in another way. Let's add another cell below this, and then we're going to run Titanic.head10, and that'll print out the first 10 rows. And what we're checking for here is to make sure that where there used to be missing values, there's now the average value of age. So let's go ahead and run that. And you could see here in this row right here, we have 29.699, and that's going to be the average value. And you can tell because the rest of the values are integers, and this one is a float. Lastly, we saw that SIB-SP and Parch both represented the size of a family, and they have a similar relationship with the target variable. So we want to combine those into one feature. Again, we talked about this last lesson, but whenever we can reduce the number of features while maintaining the information that those features provide, we should do that because it clarifies the picture for the model. So all we want to do here is declare where we want to store this new feature. So Titanic, we'll call it family count. And then all we have to do is add together the two features that we want to combine. So that's SIB-SP, add to Parch. So again, what this is going to give us a count of is the number of siblings, number of spouses, number of parents, and number of children. The last thing we have to do, and this is pretty important, is we have to drop the SIB-SP and the Parch features. Now that family count is basically representative of both of those features, they become repetitive. This creates what's called multi-collinearity. When you have multiple features that are basically accounting for the same information, in this case family size, what happens is the model has a very hard time assigning proper value to those three features since they all look the same to the model because they are so highly correlated. This can have negative consequences on the performance of the model. So that's why when you combine multiple features into one, you almost always want to drop those original features. So again, we're going to call Titanic.drop and we'll pass in a list of features that we want to drop. So that's SIB-SP and Parch. And then just like we saw above, we'll tell it axis equals 1, and we want to replace Titanic in place. And then now that that's dropped, let's print out the first 5 rows. So we can see family count here, and we no longer see SIB-SP or Parch. Just as we explored some of our continuous features back in the second and third lessons in this chapter, in the next 2 lessons, we'll explore some of our categorical features. We generally do these separately because we use different approaches for exploring continuous features than we do categorical features. Let's start by importing the packages that we'll need for the next 2 lessons and reading in our Titanic dataset. Now, just to make our data a little bit cleaner for this exploration, we're going to go ahead and drop all of the continuous features. In addition to the continuous features, we're also going to drop name because just as we saw with passenger ID, it's just a field for identification and doesn't really have anything to do with whether they survived or not. So we'll be dropping passenger ID, P-class, name, age, SIB-SP, Parch, and fare. And then again, this drop method, you'll run it on the Titanic data frame. You pass in your list of features you want to drop. You tell it we want to drop columns instead of rows. And we say, let's alter Titanic in place. So let's go ahead and run that. Now you'll see that we have a nice clean data set. We only have our categorical features left, plus our target variable. So the first thing that we want to do is explore our data at a very high level. So we're going to do that by calling this really easy info method on our data frame. Now what this is going to tell us is it's going to tell us how many non-null entries there are in each of our features, as well as the type of feature it is. So you can see for survived, it's an integer, and then the rest of these are objects or strings. But the thing that I want to call out here is that you have 891 non-null features for almost all of these, but you'll notice that cabin only has 204 non-null features, and then embarked only has 889 non-null features. So that means that we have a lot of missing values for cabin, and then just a couple for embarked. So let's dig into these missing values for cabin. So we'll add a cell below. And if you recall back to when we were looking at missing values with age, we looked at the correlation between missingness and the values of the other features to determine whether it was missing in some systematic way. So we'll do something similar, but we're going to look at its relationship to the survived field only. So again, we'll start with a group by, and we'll tell it we want to group by whether cabin is missing. So we'll do that by calling the cabin feature from the Titanic data frame. And then we'll call this isNull method. And what that'll do is it'll segment the data frame into 2 groups. One where cabin is missing, and then another where cabin is not missing. And then lastly, we just call .mean. And that will basically just generate the average value for the survived field for each of those two groups. So let's go ahead and run this, and I just want to call out two things here. This is only returning the survived field, because like we saw up here, the survived field is the only feature left in the data frame that is continuous right now. And then the other thing I want to call out is when you see cabin equal to true, that means it's missing, and then false means that it is not missing. So essentially what this table is telling us is there's a really dramatic split where over 66% of the people who have non-missing cabin values survived, while less than 30% of those who had a missing cabin value survived. Again, when we looked at age, we found that more or less age was missing at random. But in this case, it's very clear that cabin is not missing at random. It's actually a very strong indicator of whether somebody survived or not. Now, this really illustrates the value of exploring your data. Typically, if you see a field that has a missing value for 687 out of your 891 rows, you'll usually just drop the entire column because it's not really offering a whole lot of value when almost 80% of your examples have a missing value for that field. But our exploration uncovered a tremendous source of value for the model. So one easy hypothesis here is just that people without an assigned cabin literally don't have a cabin. Maybe they were stuck somewhere in the bowels of the ship, and that's why so few survived. But ultimately, the reason doesn't really matter so much as our treatment of this feature. In this case, the missing value actually means something, so we want to capture that. So the way we're going to handle that is just create a binary indicator that just says whether a person had a cabin or not. So we'll say that we're going to store this in cabin underscore ind, and we're going to use this really nice where method from NumPy. And what this where method does is it's just a simple if statement where you first pass in a condition, and our condition is going to be whether cabin was null or not. So we're just going to take the same method that we saw up here, and this will just return true or false on whether that cabin field is missing for a given example. And then the next argument is just if the condition is true, so if it is missing, then we pass in a 0 because that's indicating that they did not have a cabin. And if that condition is false, we pass a 1. And so this will just store in cabin underscore ind a 0 or a 1 based on whether they had a cabin or not. And then lastly, let's just take a look at our first 10 rows. Titanic.head, and then you pass in 10 to tell how many rows you want to look at. And let's go ahead and run that. So just to recap, we have identified that the missing values for cabin actually mean something. So we've captured that value by encoding this as an indicator variable. In the next lesson, we're going to look at some plots that will help us understand how useful the cabin indicator, the sex feature, and the embarked features are. We're going to pick up right where we left off in the last lesson. What we really want to understand in this lesson is the relationship between the different levels of our 3 categorical variables and the survival rate. This will tell us whether, for instance, women were more likely to survive than men. This will give us an idea of which features are useful and which are not. So we're going to use the same categorical plots that we used back in lesson 3, and we're going to call that on the 3 features that we want to explore. This is the exact same code that we walked through before, but just as a reminder, we're looping through our 3 categorical features, so that's cabin indicator, sex, and embarked. And then we're creating a new plot for each index for the items in our list. And then lastly, we're creating a categorical plot where we're using the feature name, plotting that against survived on the y-axis, using the Titanic data set, and we're using point categorical plots. So let's go ahead and run this. So now if you see this future warning, recall back to the prior chapter where I talked about importing that warnings library that we use to filter out these future warnings. And the future warning is just saying, hey, in a future release of this given package, and this package is SciPy, we're going to change something that you're using here. But I wouldn't worry too much about this. So moving on to the categorical plots, just as a reminder, the points here indicate the survival rate for everybody at that level, and the vertical bar is the error bar based on the sample size at each level. So looking at this first plot, this says that people without cabins had a 30% survival rate, and those who did have cabins were around 66%. So we saw this from the analysis above. But let's look at this sex feature. We see that more than 70% of the women survived, while only 20% of men survived. So it's really clear that this has really powerful splitting power. So just these two features alone have quite a bit of power, as we could see by these categorical plots. So just based on cabin indicator and gender of the passenger, you could start to imagine being able to get a really good idea of whether somebody survived or not. Again, this is the value in exploratory data analysis. Now let's look at the embarked feature. So this embarked feature has to do with where they boarded the Titanic. So C is Cherbourg, Q is Queenstown, and S is Southampton. We see that there's some pretty clear separation power here. However, this is where we need to apply a little bit of critical thinking. It's unlikely that where they boarded caused them to survive or not. More than likely, this is correlated with other features that are already being accounted for in our data. For instance, perhaps a higher ratio of men boarded in Southampton, or maybe more people that boarded in Cherbourg had cabins and thus were more likely to survive. We can actually explore these hypotheses using pivot tables. Now, if you've ever used pivot tables in Excel, they're a great tool for exploring the relationship between multiple variables. In Python, there's a really nice built-in method within pandas. So we can call that by just calling our data frame and then the pivot table method. What we need to pass in is we'll tell it to only look at the survived column, otherwise it'll look at all the columns. And then we'll say for the index, we'll use the sex column, and that basically just tells us what the row labels will be. And then we'll tell it that for the columns, we want to make those labels based on embarked. And then lastly, we need to pass in an aggregation function. The default here is mean, but we just want to look at count because we just want to look at the distribution of where people boarded based on gender. So we can go ahead and run that. And so this is telling us that 95 people that boarded in Cherbourg were male, while only 73 were female. Now you can see that for Cherbourg and Queenstown, the number of men versus women boarding is fairly close. But in Southampton, you can see that more than double the amount of men boarded as women. Given the fact that we know men were much less likely to survive than women, this would explain why Southampton had the lowest survival rate of all the ports. Next, let's look at the relationship between port and whether they had cabins or not. So our hypothesis would be that more people that boarded in Cherbourg had cabins, and that's why we saw a higher survival rate. So we can just copy and paste this line of code down here, and all we have to do is just change the index from sex to cabin indicator. And so if we run that, here we can see that for Queenstown and Southampton, there are drastically more people without cabins than with cabins. So for Queenstown, there's about 15 times more people without cabins than with cabins. And for Southampton, there's about 3.5 times more people without cabins than with cabins. But then when we look at Cherbourg, it's relatively close. Only about 50% more people had no cabin versus having a cabin. Given that we know people that had cabins were much more likely to survive, this would explain why Cherbourg had a much higher survival rate. So if we go back and look at our plot, we have now explained that fewer people from Southampton survived because so many more men boarded there, and a much higher ratio of people survived from Cherbourg because so many people that boarded there had cabins. So in this section, we've learned that cabin indicator and sex have a very strong correlation with survival, and they could be really useful features in a model. We also learned that embarked is not providing much information that isn't already covered by our other features in the model. Thus, it's repetitive and not really useful to the model. So we're going to use all of these learnings to clean up our categorical data in the next section. In this final lesson of the EDA and data cleaning chapter, we'll take what we learned through our EDA on categorical variables and we'll apply it to clean up our data set. Part of this is going to be repeating what we did in the last lesson, but we'll remove all of the exploratory work so you can see a clear, direct way of how this data should be cleaned. So we'll start by importing the packages that we need, reading in our data, and then we're going to drop the name and the ticket features. We already talked through why we're dropping name. We're going to drop ticket as well since it's essentially a randomly assigned number. We already captured ticket class with the p-class feature. So in order to drop those two features, we'll just call this .drop method, pass in a list of those two features, tell it we want to drop the columns, and we want to alter Titanic in place. So go ahead and run that. In the last section, we learned that missing values for cabin weren't missing at random, and that when people did not have a cabin, they were much less likely to survive. So we ran this exact same code in the last lesson. So we use this np.where method, which is essentially just an if statement, and it will create an indicator variable that is 1 when cabin is not missing and 0 when cabin is missing. So let's go ahead and run that, and we'll see that now cabin indicator is 0 when cabin's missing, and it's 1 when cabin is not missing. So the next thing that we need to do is we need to convert the sex feature from male versus female to numeric. Now, we didn't really talk about this at all in our exploratory data analysis stage. So just a little bit of context here. A model doesn't know what male versus female really means. All it knows is that there are two values for sex. What those values are doesn't really matter. And some types of models have a hard time handling categorical variables. So if we convert it to being numeric, it maintains those two levels, but now it's just a little bit easier for most models to handle. So this is how we're going to handle it. We're going to create this dictionary called gender_num that will handle the gender to numeric mapping, and then we'll apply that to the sex column using the .map method in pandas. So just to make it easy, we'll make male equal to 0 and female equal to 1. And so what this will do is it'll say when I see a male in the sex column, assign it a 0, and when I see female, assign a 1. And now we need to apply this using this .map method. So the way we do that is we call out our sex column, and then we call the .map method, and then we'll pass in gender_num. And lastly, we need to tell pandas where we want to store the output of this. And we'll just say assign it back to itself, essentially. So that will replace the sex column with a 0 when it sees male and a 1 when it sees female. So lastly, let's go ahead and print out the first 5 rows, and we can run that. And again, now you can see that sex is replaced by 0 and 1 instead of male and female. Lastly, now that we have cabin indicator, the actual cabin feature is repetitive and unnecessary. In addition to that, in our last lesson, we discovered that there were different survival rates for the different levels of the embarked feature. However, this was not a causal relationship. Other features like % of men boarding at each port or % of people that had cabins were the real causal factors. And since those are already accounted for in this model, we can drop the embarked feature. This also mitigates any potential impact of the multi-collinearity that I mentioned before. So we've done this before. We can actually just scroll back up here and we can copy this .drop command. And the only thing that we need to do is we just need to replace this list of features. We'll replace it with cabin and embarked. Again, we'll tell it to drop the columns and alter Titanic in place. And then just to make sure it did what we expected, we'll print out the first 5 rows. So now we can see a nice clean data set with all numeric features that'll be easier for a model to ingest. Now that we have a decent idea of how to explore and clean our data, we want to start setting the stage for building a model by understanding what it means to measure success of the model. The first step is walking through why it's necessary to split up our data before we build a model. Let's first revisit the definition of machine learning that we settled on back in the first chapter. Fitting a function to examples and using that function to generalize and make predictions about new examples. Now, again, this part on generalizing to make predictions about new examples is the core of machine learning. The model needs to learn the underlying pattern that will allow it to make predictions about future examples. You could fit a model that simply memorizes the examples that you give it, but that's not going to be very useful when it's presented with new examples. So let's revisit this linear regression model that we looked at previously. The question we're concerned with is whether this line or model will generalize to new examples, and we can't say for sure because we don't have any additional examples. But based on the data we're looking at right here, it looks like it's doing a pretty good job of capturing the underlying pattern or correlation. Now, as a counterexample, what if we have a line that's really squiggly and just runs through every single point on this plot? That would be an example of a model that's just memorizing the examples that it has seen, but never really learned the underlying pattern. Okay, so now the question becomes, how do we make sure that the model is learning the underlying pattern and not just memorizing the examples? Well, this is something that we're going to continue to talk about throughout the rest of this course. But first, I mentioned back in slide 2 that we don't know how well our model will generalize because we don't have any additional data to test how well it will generalize. We can solve that by splitting our data set into 3 separate segments. The first is called the training data. This is the data or the examples that the model will learn those general patterns from. In the previous slide, that would be all the points we see on the plot. For linear regression, like we see on that plot, the model would learn that trend or underlying pattern from the data and come up with the best fit line. Now, the second data set is what's called the validation set. And that represents the first attempt to understand how the model will generalize to new examples. So generally what will happen is we will fit a number of different models on our training data, and then we'll use this validation set to determine which models generalize best. It's important to emphasize that these models have not learned in any way from this validation set. These are completely unseen examples. So I just mentioned fitting a number of different models. And we'll talk about this more in the following lessons, but in machine learning, we typically will experiment with a variety of algorithms and hyperparameter settings. So maybe we'll test out 5, 10, 50, or potentially even hundreds of different models. And they'll all learn from the same training set, but they'll be tuned in ways to learn different things about the training set. And then we'll treat this validation set as their testing ground. So in the linear regression example we looked at before, this would be like if we gave it an instance where there was 110 millimeters of rain. The model didn't see this at all in the training set, but if it was fit well and it learned the underlying pattern, then it would be able to generalize and make an accurate prediction about the example and more broadly about the other examples in the validation set. Lastly, the test data set is used to provide an unbiased evaluation of what the model will look like in its real environment. So by this point, you fit a bunch of different models on the training data, you've evaluated them on the validation set, and you've selected the best model. The only difference between the validation set and the test set is that you used performance on the validation set to select this model as your best model. So this test set is just one more check to make sure that the performance does not deviate too much from what you saw in the validation set. Okay, so let's zoom back out for a minute. Now this can vary, but a standard way to split your full data set out is to assign 60% of the data to the training set, 20% to the validation set, and then the remaining 20% to the test set. We'll talk more about this as we move forward, but this is kind of what the high-level overall process looks like. So moving left to right, starting at the bottom of this training circle by adjusting and cleaning the features, then you train it on the training data, evaluate it using the validation data, then at this point you have a decision to make over kind of on the right-hand side of this validation data circle. If none of your models are any good based on the performance on the validation set, then you need to revisit the training phase and consider some new variables or new models. If the performance is quite good, then you can select your best model and pass it on to the testing phase. Now, if you evaluate it on the test set and performance is what you expect, then that model is ready to go. However, in rare cases, the performance on the test set may heavily deviate from the performance that you saw on the validation set. And in that case, you need to circle back and dig in a little deeper to understand what's going on here. So these two concepts are related, but the risks are that your model will overfit or underfit the data, which could lead to an inaccurate representation of how the model will generalize. We're going to dig into these concepts quite heavily in the next chapter. In this lesson, we're going to take what we learned in the last lesson about splitting up our data into training, validation, and test sets, and we're going to actually implement it. So we're going to start by importing the packages we need and reading in our data. I'll just call your attention quickly to this train test split method that we're importing from scikit-learn. That's going to make our job here very easy. So let's go ahead and run this. Now, to split into train, validation, and test set, we need to start by splitting our data into our features, and we're going to do this simply by dropping the survive field, which will then leave the fields that we're using to make an actual prediction. And then we also need to assign just that survive field to the labels. We do this simply because it's the format that the train test split method requires. So the next thing that we'll do is we'll call our train test split method, and we first need to pass in our features, and then we'll pass in our labels, and then the next thing that it requires is a test size split. So we're going to indicate we want it to be 40%, and I'll revisit that in just a second. And then the last thing we pass in is what's called random state, and that's just the initialization seed for the randomizer, not anything that we really need to discuss here. So you might be wondering why we're indicating a test size of 40% when we previously said the test set size is only 20%. The reason we're doing that is because the train test split method doesn't have the functionality to split one data set into 3. It can only split one data set into 2. So we're going to handle this in 2 steps. The first step is going to allocate 60% of the data to our training set and the remaining 40% to what they're calling a test set. And then in the second step, which I'll show you in just a second, we'll take this 40% and we'll just split it in half. And so that'll leave us with 60% training, 20% validation, and 20% test set like we talked about in the last lesson. So before we do that second step, we need to name the outputs from train test split. So it's very important to remember that this train test split is going to output 4 data sets. The first thing it's going to do is it's going to take these features and split that into a train and test set. So we'll name those x_train and x_test. And then the second thing that it'll do is it's going to take these labels and it's going to split those into 2 data sets. So we'll call that y_train and y_test. It's very important to remember that this is the exact order that it will output it in. So again, it takes the first entry, features, and splits it into train and test. Then it takes the labels and splits them into train and test. So this will give us 60% in our training set and 40% in what they're calling this test set. So let's just go ahead and copy this down, and we're just going to run this again. But what we're going to pass in instead of features and labels is we're going to take this x test, and that represents our features, and then y test, and that represents our labels. So then we'll take this test set size and we'll make it 50%. So again, we're taking the 40% that the first step assigned to what it's calling the test set, and we're taking those down here, and then we're splitting that in half, and then we just need to rename the outputs. So we'll rename this x_test, and then this will become our validation set, so x_val, and then y_test, and y_val. So let's go ahead and run that. Now just to recap, x_train and y_train should now represent 60% of our data. X_test and y_test should represent 20% of the data. And then x_val and y_val should represent the remaining 20% of our data. Now, let's just quickly take a look at the length of each of these data sets to make sure that 60% went to train and 20% to each test and validation. So the way we're going to do that is we're going to print out the length of labels, which represents our full data set. Then we'll look at the length of y_train, and that should be 60% of our full data set. Then we'll look at the length of y_val, which should be 20%, and lastly y_test, which should be the remaining 20%. And so you do see that that is the case. And I'll just call out that we do have a different number assigned to the validation set than we do the test set, even though they're each supposed to be 20% of the full data set. The reason for that is we just had on number that then we were trying to split in half. And so one extra observation got assigned to the validation set. But this is how you'll take your full data set and split it into 60% for your training set, 20% for your validation set, and 20% for your test set. So we've been talking about using training, validation, and test set to measure our model's ability to generalize. In this lesson, we're going to add one additional layer on top of our evaluation framework with something called cross-validation. We're going to dive into cross-validation in this lesson, and then the next lesson, we'll zoom back out and put all the pieces together. Let's start with a couple of quick definitions, and then we'll walk through an example. So a holdout test set is essentially a generalization of the test set that we've been talking about. It's just any data set that was not used in fitting a model that is set aside for evaluating the model's ability to generalize. So with that idea, both the validation set and the test set that we've been talking about both qualify under this general term of holdout test set. The next definition is a new one, k-fold cross-validation. This is a process by which data is divided into k subsets, and the holdout test method is repeated k times. Each time, one of the k subsets is used as the test set, and the other k-1 subsets are combined together to be used to train the model. This is another tool that is really helpful to gauge a model's ability to generalize to unseen examples. Let's look at an example to see if we can clarify this a bit. So in this example, we'll start with a full data set of 10,000 examples, and let's just say we want to run 5-fold cross-validation. So in other words, k in k-fold is equal to 5. So the first step is to split those 10,000 examples into k, or 5, subsets. So you'll see now we have 5 subsets of data. Each has 2,000 examples. So I just want to clarify that this is sampling without replacement. So no single example will appear in 2 different subsets, and all original 10,000 examples are still accounted for in these subsets. And these subsets will remain the same throughout this entire process. So an example in subset 1 will remain in subset 1 all the way through to the end. So now we assign one of these 5 subsets as a test set, it's indicated in red here, and the other 4 indicated in blue are the training set. Now we'll fit a model on the training set of 8,000 examples in blue, and then we'll evaluate the model on the 2,000 example test set, and then we're going to record the performance metric. So to be clear, this is all handled under the hood in scikit-learn. You don't have to manually implement any of these steps, but it is really useful to understand what is actually happening and why we use this. After the first iteration, it will store the model's performance on that holdout test set. So here we're saying that's 0.867. So in other words, it was able to generalize and make a correct prediction on 86.7% of these examples that it did not see during training. Okay, then next we'll move on to the second iteration, where now the 4th subset is the test set, and then 1 through 3 along with the 5th subset represent the training set. Now we'll refit a brand new model on these 8,000 training examples and evaluate it on the 2,000 test examples. And then we'll store the performance metric. Here we're saying that's 0.884. So again, we're just saying that this model was able to generalize and make a correct prediction on 88.4% of the examples that it did not see during training. Then again, in the 3rd iteration, the 3rd subset will be our test set, and then the model will be trained on the 8,000 examples in the 1st, 2nd, 4th, and 5th subsets. We'll train a model on those subsets, evaluate it on the 3rd subset, and store the performance metric of 90.1%. We'll do the same thing again for the 4th. Same process as before, but now the 2nd subset is our holdout set. And last but not least, the 1st subset is our test set, and 2 through 5 are our training data. Fit a model, evaluate it on the 1st subset, and store the evaluation metric. Now, it's worth noting that at this point, every subset, and thus every example, has been used in the training set 4 times and the evaluation set once. So we've now used this algorithm configuration to fit on all different combinations of these examples, and we've evaluated it on every single point in the data set without training on that point. So you can see how this would be a really powerful tool to gauge a model's ability to generalize. Okay, and then lastly, you can either output the full array of scores that you see here, or you can just output the average across the array. Either way, this gives us a more robust gauge of what the outcome would be, since we've now tested this model configuration's ability to generalize on every single point in this data set. Now, let's just say we're using a single holdout test set, and using that to gauge the performance of this model that we're going to use for our business. Now, from the lowest score to the highest, so from 86.7% to 90.1%, that's a difference of 3.4%, which may not seem like a lot, but in a business setting, this could potentially impact thousands or even millions of dollars. So, having a read on how this model performs over 5 separate test sets is a leg up on truly understanding our model performance instead of getting a read on how it generalizes to just a single test set. So this gives us more confidence to understand how the model is performing and even a range of plausible outcomes or simple error bars on the projection. In this lesson, we're going to start to pull everything together into a cohesive framework that will be used for evaluating our model. Now, there are 2 components of an evaluation framework. First, there's the evaluation metrics. How are we gauging the accuracy of the model? What is the quantitative measure of performance that we're going to use? Secondly, there's the process. How will we leverage our full data set to mitigate the likelihood of overfitting or underfitting, both of which will impact the model's ability to generalize? What are the evaluation metrics that we'll use for our Titanic data set? It's important to note that this is what's called a classification problem. We're just making a binary prediction. Did they survive or not? Rather than trying to predict some continuous number, like the number of umbrellas sold. That's what's called a regression problem. So, for a classification problem, we're going to use 3 commonly used evaluation metrics. The first is accuracy. This is very straightforward. It's just how many did the model predict correctly divided by the total number of examples. The next evaluation metric is something called precision. This is going to be the number of people that the model predicted to survive that actually survived, divided by the total number of people the model predicted to survive. In other words, when the model said somebody survived, what % of the time was it correct? And then the next metric is something called recall. And this is a nice complement to precision. So this is the number of people that the model predicted to survive that actually survived. So again, this is the same numerator as you saw in precision, but the denominator is the total number that actually survived. So in other words, if somebody actually survived, what % of the time did the model predict that they survived? So just to recap, the numerator is the same in both precision and recall. It's just the denominator that is different. So if you're more of a visual person, perhaps this image might be helpful to better understand. So I'm going to convert the terminology used in the image to align with the Titanic data set. So every little dot in this box is a person on the Titanic. Everything on the left would be people that actually survived. Everything on the right would be people that did not survive. So everything inside the circle would be people that the model predicted to survive, while everything outside the circle would be people that the model predicted would not survive. So precision is going to be the dots inside the left half of the circle. So again, this is people that the model said survived that actually did. And then you'll divide that by the entire circle because that's all people that the model thought survived. While recall is again the dots inside the left half of the circle, people that the model said survived that actually did, divided by the whole left side of the box. That's people that actually survived. So now, we covered evaluation metrics. Now the second component is the process. Now we saw this diagram back in lesson 1 in this section. So again, we take our full data set, we put 60% of the examples into the training set, 20% into the validation set, and 20% into the test set. Now I'm going to add one more wrinkle here. Recall cross-validation that we discussed in the last lesson. Now we're going to be splitting up the training set into 5 groups to run 5-fold cross-validation. So now what does this look like from a high level? This will become more clear in the final section when we run this full pipeline with the Titanic dataset. But just to get a view for the whole process, the first step is we'll fit and test numerous candidate models using 5-fold cross-validation on the training set. Again, in the last section, we discussed how that will output a single performance metric or an array of metrics, and we'll use that information to determine the best few models. Then we'll refit those algorithms with the chosen hyperparameter settings on the full training set, and then we'll evaluate them on the validation set. Using that performance on the validation set of unseen examples, we'll select the single best model. And then lastly, we'll use that model to evaluate it on the test set to get an unbiased view of its ability to generalize to unseen examples. In this chapter, we're going to be discussing model optimization. In this lesson in particular, we'll be setting the foundation by discussing the bias-variance trade-off. So what do we mean by bias and variance from a conceptual level? We're going to use a dart analogy because it offers a nice visualization of what bias and variance represent. So we'll start at the top left, and we'll rotate around clockwise. So at the top left, we have low bias and low variance. That means you're centered around the bullseye and you are consistently hitting that bullseye. So this would be like a pro dart player you see on TV. Rotating to the top right, this would be low bias, but high variance. This means you're centered around the bullseye, but you're not consistently actually hitting the bullseye. So breaking this apart, low bias dictates that you're centered around the bullseye, and then the high variance dictates that you're spread out and not consistently hitting whatever you're aiming for. This would be like a fairly good dart player, but not quite good enough to consistently hit that bullseye. Now rotating around to the bottom right, to high bias and high variance, this means that you're not centered around the bullseye and you're spread out. This is what it looks like when I'm playing darts. Finally, the bottom left is high bias and low variance. This means that you're not centered around the bullseye, but the darts are fairly concentrated. So this would be either somebody that's a little bit confused about what they should be aiming for, or maybe it's a pro dart player that's aiming for that triple 20 or something other than bullseye. Okay, so now moving into something a little bit more concrete and actually pertaining to machine learning. So bias in machine learning is the algorithm's tendency to consistently learn the wrong thing by not taking into account all of the information in the data. High bias is a result of the algorithm missing relevant relationships between the features and the target variable. So using our dart analogy, we're missing the target. The model doesn't really understand what it should be aiming for, and as a result, its predictions are consistently off base in a systematic way. So now looking at variance, variance has to do with an algorithm's sensitivity to small fluctuations in the training data. High variance is a result of the algorithm fitting to random noise in the training data. So again, in our dart analogy, this means that the dart throws are extremely imprecise. One throw could nail the bullseye, and the next could be way off, maybe even missing the board. This means that the model is very, very highly tuned to the data that it's seen already, perhaps even just memorizing examples that it's seen, so it can absolutely nail predictions for examples that look identical to what it's seen before, but it does very poorly on examples that look nothing like what it's seen before. Lastly, this slide will set the stage for our discussion in the rest of this chapter. So don't worry if you don't understand the ins and the outs of this plot right now, but what I want you to see in this plot is that model complexity is across the x-axis, so you have complex on the right and very simple on the left, and then model error is on the y-axis. Then we have this teal line that represents the variance, and that consistently increases as the model gets more complex. So more complexity means higher variance. Then we have this red line that represents bias, and bias decreases as the model gets more complex. So again, less complexity means high bias. And then lastly, we have this black total error line, which is very high for both a very simple model and a very complex model. And then it bottoms out somewhere in the middle where you'll see that vertical line that says optimum model complexity. So this is what bias variance trade-off is all about. Finding the right model complexity that minimizes both bias and variance as much as possible. So if you only focus on minimizing bias, you'll have very high variance. If you only focus on minimizing variance, you'll have very high bias. The goal is finding that appropriate trade-off of bias and variance to reduce the overall error as much as possible. So if you're not a visual learner and you do better with equations, total error is going to be bias plus variance plus some irreducible error. All that irreducible error is some amount of error that the model will never be able to learn. So that's randomness or noise or however you want to define it. The part of this equation that we control is the bias and variance, and reducing those will directly reduce total error. So this slide will help us pull together all the different concepts that we'll learn over the next few lessons. In this lesson, we're going to talk about a concept that we've briefly mentioned previously in this course, and that's the problem of underfitting. Recall this plot and equation from the last lesson. Total error is the sum of bias, variance, and some irreducible error that we can't control. The left side of this plot represents underfitting. Notice that we're talking about a low complexity model where we have low variance, but we have high bias, which results in high total error. Again, recall that we defined bias as the algorithm's tendency to consistently learn the wrong thing by not taking into account all of the information in the data. High bias is a result of the algorithm missing the relevant relationships between features and target outputs. And finally, that translates to mean that underfitting occurs when an algorithm can't capture the underlying trend of the data. Now, to get a little bit more tangible, this is what underfitting looks like in a classification problem. To apply this plot to the Titanic dataset that we're working with, imagine if this plot had age on the x-axis and fare on the y-axis. Then imagine that the circle means that individual person survived, and the X means that that person did not survive. So this plot would be telling us who survived and who did not based on age and fare. And then the line drawn on this plot would be our model. It's what's called the decision boundary. So every person to the left of the line, the model would say that they would survive, and everybody to the right, the model would say they would not. Now this model looks a little bit too simple. It looks like it's not really picking up on the pattern of the data. Taking a step back, we can kind of see that the survivors are kind of clustered in a semicircle on the bottom left. So ideally, we would have a model that kind of generates a line that curves around that semicircle. And this model just assigned a straight line for the decision boundary. You'll really notice the difference as we get into overfitting and understanding what that looks like, and then when we circle back to finding the optimal trade-off. So lastly, just to summarize, underfitting occurs when an algorithm cannot capture the underlying trend of the data. And that happens when we have a model that is too simple with high bias and low variance, which results in a high total error. In this lesson, we're going to talk about another concept that we've briefly mentioned previously. This problem is on the opposite extreme of underfitting, and not surprisingly, this is called overfitting. Once again, recall this plot and the equation from the last two lessons. Total error is the sum of bias, variance, and some irreducible error that we can't control. We learned in the last lesson that the left side of this plot represents underfitting. On the other extreme, the right side of this plot represents overfitting. So we're looking at a very complex model where we have low bias, but high variance, which drives high total error. Revisiting prior definitions, variance refers to an algorithm's sensitivity to small fluctuations in the training data. High variance is a result of an algorithm fitting to random noise in the training data. And overfitting occurs when an algorithm fits too closely to a limited set of data. In other words, the model might just memorize the examples that it has seen in the training data. So then when it sees a new example that looks a lot like an example that it's already seen, it can make a very accurate prediction. But then if it sees a new example that looks nothing like any other example it's seen before, it will likely make a very poor prediction because it didn't learn the underlying pattern, it just memorized examples. So that's where we get this term high variance, where some predictions might be very accurate and others might be very, very poor. So remembering what we talked about last time, Imagine age on the x-axis and fair on the y-axis. A circle here means that the person survived, and an X means that they did not survive. So the line drawn on this plot would be our model or our decision boundary. So every person within that group to the left of the model would say that they survived, and everybody to the right did not. So this is what overfitting looks like. Recall back to the plot we saw on the first slide, where we said a very complex model is one that is overfit. Now we can see on this plot here that there's a very complex decision boundary compared to the straight line we saw with underfitting in the last lesson. So this model has fit very closely to the training data, and it's very likely that this isn't the real pattern that it should be learning. Instead, it's just memorized these examples. As a result, the model will have a very hard time generalizing to unseen data. That is overfitting. So to summarize, overfitting occurs when an algorithm fits too closely to the training set and just memorizes examples. This results in low bias and high variance, which drives high total error. In the last few lessons, we've talked about bias, variance, underfitting, and overfitting. In this lesson, we're going to put all of these concepts together to try to explain what it means to find the optimal trade-off to minimize that total error. So let's revisit this plot just one more time. It highlights that underfitting is on the left, overfitting is on the right, and it calls out that there's some optimal model complexity right in the middle where we have an ideal trade-off between bias and variance to achieve minimum total error. That's what we're trying to find. Now let's look at this in a slightly different way. Just looking at a scale of complexity, we have this very simple model. The simple model will underfit our data and won't learn the true pattern. And based on the plot in the prior slide, we know that this means high bias and low variance. Now on the other extreme, we have an overly complex model. This model is overfitting and essentially just memorizing the training set. And we know this means low bias and high variance. Now the goal is to find something in the middle. This would have some kind of medium complexity. It would learn the true pattern in the data with this kind of curved decision boundary, but not memorizing every example in the training data. And this would have low, not minimum, but low bias and low variance. So again, just overlaying this with the other plot, on the left side we have low complexity and underfitting, on the right we have high complexity and overfitting, and then in the middle we have some optimal complexity with the right decision boundary with low bias, low variance, and low total error. Now just summarizing this in table form. This is everything that I just said, and keep in mind this is all relative. So the right model might actually be quite complex, but it's not as complex as the overfit model. Now, up to this point, we've been talking entirely about attributes of an underfit or overfit model, but we haven't really talked much about how to really identify them. Sure, high variance means an overfit model, but how do we identify high variance? This plot illustrates how to identify it. So this is showing training and test error across different levels of complexity. On the left side of the plot, we have an underfit simple model. In the middle is a medium complexity good model, and on the right, we have an overly complex overfit model. So what this plot shows is that for an underfit model, we'll have high training error and high test error. A good model will have low training error and low test error. And then an overfit model, we still have low training error, but now it gets to the point of memorizing the training set, and so its performance on unseen examples in the test set really suffers. So lastly, here are these takeaways in a table form. This is how you can diagnose overfit versus underfit. Typically, you'll really only look at the test error. So if you see a low test error, then generally that means that you have a good model. If you have high test error, you can look at the training error to really understand whether you're overfitting or you're underfitting, and then you can work from there to improve your model. Over the last few lessons, we've been slowly putting all the pieces together. We'll continue that in this lesson as we talk about how hyperparameter tuning can help you achieve the right bias variance trade-off. So we've defined underfit and overfit, and now we understand how to identify it using the insights from this plot. But what we haven't really talked about is what actually causes it to happen and how we can fix it. That's where hyperparameter tuning comes into play. So there are actually two methods to tune a model for optimal complexity. The first is hyperparameter tuning. That's choosing a set of optimal hyperparameters for fitting an algorithm. So this is what we'll cover in this section, including defining what a hyperparameter actually is. The second is regularization. This is a technique used specifically to reduce overfitting by discouraging overly complex models. And we'll cover this in the next lesson. Okay, so let's start with some definitions, and then we'll walk through an example. The first thing I want to do is distinguish between a parameter and a hyperparameter. So a parameter is a configuration variable that is internal to the model, whose value is estimated from the data. That last piece is really the key. A parameter is estimated from the data. Okay, so now we'll see how that's different from a hyperparameter. A hyperparameter is a configuration that is external to the model, whose value cannot be estimated from the data, but whose value guides how the algorithm learns parameter values from the data. Okay, so hopefully that makes some sense, but I'll try to clarify what this means through an example. We're going to use a very simple decision tree to determine if somebody survived on the Titanic or not. So the first thing you'll do is you'll take one person from that Titanic data set, and we'll ask whether they're male or female. We're just going to explore the male side of this decision tree first, and then we'll circle back to the female side. So the next question would be whether their fare was over $20 or not. So if it was more than $20, then this model would predict that they survived, and if it was less than $20, then the model would say that they didn't survive. We know that men were less likely to survive than women, but we also know that people with higher fares were more likely to survive than those with lower fares. So now onto the female side of the tree. The second question on the female side of the tree is whether their ticket was third class or not. If it was third class, then the model would predict that they did not survive. If they were not third class, so in other words, if they were first or second class, then it would predict that they survived. Again, from our exploration, we know that women were more likely to survive than men, and also people with first or second class tickets were more likely to survive. Okay, so using this example, what is the difference between parameters and hyperparameters? Again, parameters are values internal to the model that are learned from the data. So that would be something like the $20 cutoff for fare. That branch in the decision tree could have been whether they had a cabin, or it could have been their age. But the model determined that fare is very important. Not only that, but it used the examples in the training data to determine that $20 is the optimal cutoff point to determine who survived and who did not. In addition to that, the model determined that ticket class matters, and it determined that third class is the optimal cutoff. That's another example of a parameter. Now that we know what a parameter is, what is a hyperparameter? Again, a hyperparameter is external to the model. It isn't learned from the data, but it is used to guide how the model is built. And these are defined before you fit the model to any training data. So hyperparameters for a decision tree would be something like the maximum depth of the tree or features to consider. So this tree is an example of a tree with a depth of 2, meaning that there are 2 layers of splits here. If we set it to have a maximum depth of 3, we would add an additional layer with additional splits to determine who survived or who did not. If you were in the situation where you have thousands of features to consider, you might also tell these decision trees to only select from these 10 or 20 features. So again, that would be another example of a hyperparameter. So these are things that you set beforehand that guides how the model is fit, and it can lead to underfitting or overfitting. For instance, if we set the maximum depth to 1, where the model had to decide whether somebody survived or not based only on whether they're male or female, then that would be underfitting because it'd be far too simple. But if we set the maximum depth to 500, then essentially that means it can create 500 layers of splits. And it would basically create enough splits where it could tailor the model to every individual example. In other words, it would be memorizing the training set, and that would be overfitting because the model's far too complex. Now, we've been talking about tuning hyperparameters in order to optimize the bias-variance trade-off and thus minimize total error. So this is a plot similar to what we saw in our first slide. So we have training error in light green, and we have test error in orange. On the x-axis, we have maximum depth of the decision tree. Maximum depth in this case is a proxy for model complexity. You can see with very low maximum depth, this is a very simple tree, both training error and test error are quite high. Then around a maximum depth of 9, test error bottoms out, and test and training error are relatively low. And then after that, you see the test error start to increase. So that indicates that a max depth of 11, 13, or 15 is too complex and it's overfitting. One last thing I want to mention here is that there's a tool called grid search in scikit-learn that helps us do this hyperparameter tuning. We're going to explore that more in the next chapter. In the last lesson, we talked about hyperparameter tuning as a method to avoid underfitting and overfitting. So we could explore different settings of maximum tree depth for a decision tree to determine which setting gives us the best model. In this lesson, we're going to focus on another way to tune model complexity called regularization. As we mentioned in the last lesson, regularization is a technique used to reduce overfitting by discouraging overly complex models in some way. Now, the ultimate goal of regularization is really just to allow enough flexibility for the algorithm to learn the underlying patterns in the data, but to provide some guardrails so it doesn't overfit and memorize the training data. Now, at this point, I want to introduce a principle called Occam's razor. And you may have heard of this before. It's not strictly a machine learning principle. It basically says to choose the most simple answer to a problem whenever you can. So in our case, that means choose the most simple model possible that will provide accurate predictions. So don't overcomplicate things. Again, this is what regularization will do. It provides guardrails so the model won't get more complex than it really needs to be. There are many, many different flavors of regularization, but there are just a couple examples that I want to walk through quickly. The first example is actually two techniques lumped together. That's ridge regression and lasso regression. These are variations of the same principle. In linear regression, these methods will add a penalty to the loss function that basically constrains the coefficients. In other words, model performance needs to improve a lot in order for the method of regularization to allow the model to become more complex. The second example is called dropout. This is used in deep learning, which we talked about before as being a connected series of nodes, where each node is responsible for something very specific. Now, you can imagine how this could lead to overfitting, where a given node is so focused on one task, it ends up just memorizing the examples. What dropout does is it just ignores certain nodes during the training, which will then force the other nodes to take on the responsibility for learning what those nodes that were dropped were responsible for. Now you have less specialization among the nodes, meaning that each node can generalize a little bit better, and it really tends to help with the problem of overfitting. Welcome back to the final chapter of this course, where we're actually going to dive in and get our hands dirty by building an end-to-end machine learning pipeline. Before we dive into the code, I first want to lay out the high-level process that we'll walk through in the next few lessons. Nothing here should surprise you. We've talked about every component so far. This is just pulling all the pieces together and aligning on what the rest of this chapter will look like. You should be familiar with this diagram that we looked at previously. We have our training set that represents 60% of the full data set, and that's split into 5 segments for the purpose of 5-fold cross-validation. Then we have our validation set, which represents 20% of our data. And lastly, we have our test data set, which represents the final 20% of our full data set. The first step is going to be exploring the data to really understand the type of features we have, what they look like, what their shape is, how they relate to each other, and how they relate to the target variable. Then we'll use some of those learnings to clean up our data. Again, this is all done on the full data set. Then we'll split our data into the training, validation, and test set. The next step will be using 5-fold cross-validation to fit an initial model to see what we can expect for baseline performance. The next step will be using 5-fold cross-validation to explore a number of different algorithms with different hyperparameter settings. Then we'll select the top few models and evaluate them on the validation set. At this stage, we'll dive into the results a little more than we did using cross-validation to really determine which models are performing best. Then lastly, we'll select the best model based on the validation set performance, and we'll evaluate it on the test set to get an unbiased view of how we can expect this model to perform on completely unseen data. In this lesson, we're going to clean up our continuous features by putting together everything that we learned and practiced back in the chapter on exploratory data analysis and cleaning. And then the next lesson, we'll clean up our categorical features. Now, just as a reminder, we're using this commonly used Titanic dataset that contains information about 891 people on board the Titanic with the goal of using that information about the passengers to build a model to predict whether each person survived or not. Now, start by importing some of the libraries that we'll need, and then we'll read in the data that's stored in our exercise file directory using Panda's read CSV method. We go ahead and run that and get a view of our data that we'll be diving into. Now, just as a refresher, we can call this titanic.isNull.sum method, and that will count up all the missing values in the Titanic dataset. Now we can run that, and I just want to highlight the fact that there's 177 missing values for the age feature. And we found back in the exploratory data analysis chapter that these seem to be missing mostly at random. Now, because those values are missing at random, we can replace the missing values with the average value of the age column. And we can do that by just calling the age feature, calling this fill_NA method, and then we just have to pass in what we want to fill it with. So we'll say Titanic, call the age column, and then just do .mean. And that'll grab the average value of the age column, and then we'll just tell it in place equals true to tell it to alter the Titanic data set right in place without creating a new data frame. So let's go ahead and run that. Now, moving on as a quick refresher, we looked at these categorical plots back in the plotting continuous features lesson in chapter 2. We learned that SIB_SP and parch have the same relationship to the target variable. Again, what we do here is we're looping through SIB_SP and parch, and for each iteration through the loop, we're telling matplotlib to create a new plot, and then we're calling the categorical plot method from Seaborn using the column that's coming through in each iteration of the loop and plotting that against the survival rate. So let's just go ahead and run that to get a quick recap of what this looks like. And again, we see this future warning that we've seen a couple times before that's just letting us know that in the future there will be some change that is impacting our code right here, but it's nothing to worry too much about. And so again, just to recap, we're seeing this downward trajectory where if we have more siblings or spouses, we're less likely to survive. And we see the same thing with parch, which is the number of parents and children. So back in chapter 2, we made the decision that we're going to combine these two features into one feature. And we simply do that by assigning them to the family count feature and just adding these two columns together. So we can go ahead and run that. And the last step here is we just need to drop SIB_SP and parch because the value that they're providing will be captured by the family count feature now. And leaving all three of those together could create some multi-linearity issues where the model isn't really sure where to attribute the value since they all look really similar. And then also, we're going to drop the passenger ID feature because that's an identifier with no implication on whether somebody will survive or not. So the way that we do that is we pass in the list of features. We say axis equals 1, which just tells it we want to drop the columns, not trying to drop rows. And then we tell it to alter Titanic right in place. So let's run that. And then I'm going to go ahead and print out the first 10 rows. There's a couple things I just want to call out here. At row 5, you'll see a missing age value that was replaced by the average value of that column, which is 29.699. You'll also notice that we now have a family count feature, and you'll notice that passenger ID, SIB_SP, and parch are all gone. The last step here is just to take that clean data set, and we're going to write it out to Titanic_cleaned. Now, first, we just need to make sure we write it out to the same directory, which is going to be the directory where the original Titanic dataset lives. And I'll also call out that we're passing in this index equals false argument. The reason for that is if we do write out the index, when Pandas goes to read it in the next lesson, it will think that index is actually a feature, and so it'll add a column for it. So now that we've written this clean data set out to the directory where our original Titanic data set lives, in the next lesson, we'll pick that up and we'll walk through and we'll clean up all the categorical features. Let's pick up right where we left off in the last chapter by reading in our data set that has all the continuous features cleaned, and then we'll dive into cleaning up the categorical features in this lesson. So we can go ahead and run that first cell, and let's start by creating an indicator variable for the cabin feature. Now, back in the Exploring Categorical Features lesson, we learned that unlike age, cabin is not missing at random. We learned that 2/3 of people aboard that had cabin survived, while only 30% of those aboard that did not have cabin survived. So we're going to create this really simple cabin indicator using the where method from NumPy that acts as an if statement. So the condition we want to use is whether cabin is null. So we'll call Titanic bracket cabin, and then again we'll use this isNull method, which just returns a true or false based on whether cabin is missing or not. And so we'll say if cabin is missing, we want it to return a 0, and if it's not missing, we'll return a 1. And then we'll assign that to cabin_end, and we can go ahead and run that. Next, we want to convert the sex feature from male versus female to numeric. As we discussed previously, a model doesn't know what male versus female really means. It just knows that there's 2 values for the sex feature. What those values are doesn't really matter. So if we convert it to being numeric, it just makes it a little bit easier for most models to handle. So we have a dictionary here named gender_num that does the mapping for us. So in other words, this is going to tell Pandas that if it sees male, assign a 0, and if it sees female, assign a 1. So let's do this mapping. So in order to do that, we'll call Titanic bracket sex, and then we do .map, and then we'll pass in the dictionary that dictates the mapping. So that's gender_num. And then we'll just assign this back to the sex column, so we'll basically just replace it. We can go ahead and run that. And then the last thing we need to do is just drop our unnecessary variables. So back in the plotting categorical features section, we discovered that there are a number of different survival rates according to the different levels of the embarked feature. However, we also learned that this was not a causal relationship. Other features like % of women boarded at each port or % of people that had cabins were the real causal factors. And since those were already accounted for in this model, we decided to just drop the embarked feature. Once again, that also mitigates any potential impact of multiclinearity. So we're going to drop this cabin feature because we already created the cabin indicator, drop the embarked feature, and then we're going to drop the name and ticket features as their identification variables without any real determining power on whether somebody survived or not. So we'll pass those in as a list, tell to drop the columns, and alter Titanic right in place. And then we'll print out the first 5 rows. So again, you'll notice the cabin, embarked, name, and ticket features are all gone, and you can see our cabin indicator here, and our sex feature is now, instead of male and female, there's 0s and 1s. Lastly, we just want to write out this clean data set, and we're actually going to overwrite this Titanic_cleaned. So what exists there right now is the Titanic data set with just the continuous features cleaned. We picked that up in this lesson, and we also cleaned all the categorical features. So now that the Titanic data frame represents the fully cleaned data set, we're going to write that out, and we're going to overwrite the Titanic cleaned data set that's already there. And we're going to pass in this index equals false, which again is just indicating that we want to ignore this first row. So we'll write this out so that then in the next lesson, we can pick this up so that we can split out our data into our 3 data sets and prepare to build a model on it. Now that we have our clean data set, this lesson should be quite simple. We're just going to split up our full data set so that we have 60% of our examples in the training set, 20% in the validation set, and 20% in the test set. So we'll import the packages that we'll need and read in our data. Again, we're using this train test split method that we're importing from scikit-learn, and this is going to make our job very easy. I also want to call out that we're reading in this Titanic clean data set that we created in the last lesson rather than the original titanic.csv. So we'll go ahead and run that cell. Now, as we saw previously, we'll start by splitting our data into our features by just dropping the survived column. So that will just leave the fields that are used to make our prediction. And then we'll grab our labels here by just grabbing the survived column. I'm just going to highlight again before we jump in that this is going to be a two-step process. The first step, we'll set aside 60% for our training set. And then the second step, we'll split up that remaining 40% into 20% in the validation set and 20% in the test set. So we'll call this train test split method. And first, we just need to pass in our features. Then we'll pass in our labels. Then we need to tell it how much we want to set aside for our test set. So this first step will set aside 40%. And lastly, we'll just set this random state, which is just the initialization seed for the randomizer. Now, don't forget that the ordering of these outputs is very important. So remember, first it takes the features and splits that into train and test, and then it'll take the labels and split those into train and test. So we'll label these X train, X test, Y train, and Y test. So now we have 60% in our training set and the remaining 40% into what we're calling the test set. So let's just copy this code down and we'll do the second step where we're just going to be taking this X test as our features and Y test as our labels and take this 40% that we set aside and just split it in half. So now we're going to have half go into our validation set and half go into our test set. Now lastly, we just need to update the output names. So name this X test, X val, Y test, and Y val. Now let's quickly take a look to make sure that 60% went to our training set and then 20% to each our validation and test sets. In the previous lesson, we just looked at the lengths. This time we're actually going to look at the percentages. So what we'll do is we'll create a loop where we'll be looping through Y train, Y val, and Y test. And in each iteration through the loop, we're going to be printing out the length of that individual data set divided by the length of the labels. Length of the labels represents our full data set. And then the last step, we're just going to go ahead and round this to 2 decimal places just to make the output a little cleaner. So let's go ahead and run that, and you can see that this confirms that for the first iteration, for Y train, it is 60%, and for Y val, it's 20%, and Y test, it's 20%. Lastly, let's just write out all of our data to save ourselves from having to recreate these data sets in each lesson moving forward. Now, as we saw before, we're just going to call this great toCSV method from pandas. And again, the other thing that I'm going to call out is we're including this index equals false argument so that the index doesn't get written out as a new column in each CSV file. Now in the next lesson, we can go ahead and pick these up and get to work on actually building our model. Now that we have clean data split into training, validation, and test sets, in this lesson, we're going to fit a single basic model using cross-validation. The goal is just to get an understanding of what the baseline level of performance might look like. Now remember, this phase is going to take place on only the training set. So we'll go ahead and import all the packages we need, which will include random forest classifier from scikit-learn, that's the algorithm that we'll be using, and cross-val score, which will help us run our cross-validation. Also, we're going to import this warnings module that we saw before, and we're going to tell it to filter future warnings. Now, as we saw before, this will only suppress warnings in the future class. The reason we're going to do that for this lesson is because the default value for one of the hyperparameters in random forest classifier is going to change in a future version of scikit-learn. So it just wants to let us know, but it's not really going to impact what we're doing in this chapter. So again, we're just telling this warnings module to please suppress that future warning. So then we can go ahead and read in our features and labels from our training data that we wrote out in our last lesson. Now, just as a refresher, this diagram outlines what cross-validation looks like. 5-fold cross-validation will split our training set into 5 subsets, and then it will iterate through the data 5 times each time fitting a model on 4 subsets and evaluating on the 5th subset. So in the end, each subset of data, and thus every example, will have been used to train the model 4 times and evaluate the model once. Then at the end, we'll get an array with our model scores for each of the 5 folds. So the first thing that we need to do here is instantiate our random forest classifier. And we're going to store it as RF. Now I'll just note that we could pass in hyperparameters here, but we'll choose to leave the parentheses empty for now, and that will change in the next lesson. Now, the only thing we have to do here is we'll call cross-fail score, and then we need to pass in our model, pass in our training features, pass in our training labels, and then tell it how many folds we want to do. So again, this is 5-fold cross-validation. And then we'll just tell it to output everything to scores. Now, before I run this, I'm going to tell you that scikit-learn is going to throw another warning. And again, this is not in the future warning class. So remember that warnings package is only suppressing the future warnings. This is only a warning though, it's not an error. So our cross-validation will still complete. It's just scikit-learn telling us something that thinks we should know. So let's go ahead and run this and see what it's actually going to tell us. The first thing I'll point out is it's throwing an identical warning 5 separate times. And the reason it's doing that is because scikit-learn is fitting 5 random forest models within this 5-fold cross-validation. Now, what this warning is saying is it's basically letting us know that scikit-learn would really like our labels to be in an array, but we're passing in a pandas column vector. So this is simply an efficiency issue, so scikit-learn is just letting us know in case we want to fix it. With the size of the data we're using, it really doesn't make a difference, but just to appease scikit-learn and to save ourselves from having to see this warning in every lesson moving forward, let's just go ahead and fix it. So all we need to do to convert this from a pandas column vector to an array is we'll just call .values and lastly ravel. And we don't need to go into detail on this. All you need to know is that I'll just convert it from a column vector into an array. So now we can go ahead and run it, and now we don't get that error. Now, this cross-fail score method handled everything in that diagram under the hood. So as you can see, it's really easy to use. We just have to pass in a couple things. Now let's go ahead and print out these scores. So again, it gives us an array of 5 different scores where we're getting 1 score for each of the 5 folds. You can see that the average here is probably somewhere right around 82%. But the great thing about this is that it shows you the accuracy when training and evaluating on different subsets of the data. So we can say around 82% accuracy, but depending on the subset trained and tested on, that could be as low as 79% or as high as 85%. Now, for instance, if we had only fit it on 1 training set and evaluated it on 1 test set, maybe we would get an accuracy of 79%, but we would have no idea what a reasonable range might be, and we wouldn't know if it was overfitting to this one particular subset of data. So maybe we would assume that 79% is the average, but maybe it could go as high as 90% or as low as 70%, depending on what data we're training and testing on. We wouldn't really know. So that's just one of the benefits of cross-validation. Now, in the next lesson, we're going to add one more layer to actually seek to optimize this model and beat this baseline performance. In this lesson, we're going to build off what we did in the last lesson by still using cross-validation on the training set, but now we're going to add one more layer. We're going to run grid search to find the optimal hyperparameter settings for our model. So we already set a baseline of what we can expect for performance in the last lesson. We saw an average around 82% accuracy with individual runs as low as 79% and as high as 85%. And that was just using the default hyperparameter settings for random forest. Now in this lesson, we're going to try and find the optimal model that beats that baseline performance. So looking at our imports, we're going to import this random forest classifier again, but now you'll notice that instead of using cross-fail score like we did in the last lesson, that's replaced by grid search CV. And all grid search CV is a wrapper around cross-fail score that allows us to run grid search within cross-validation. So we can just go ahead and import those packages and read in our training features and labels. The grid search CV method stores a lot of information about model performance, but it can be kind of difficult to pick through that to find what you really need. So I wrote this quick little function just to help us print out the results a little more cleanly. I'm not going to go through it in detail, but in essence, what it does is for every hyperparameter combination, it will print out the average accuracy score across the 5 folds and the standard deviation of the accuracy score across those 5 folds. So this will give us all the information that we need to select the optimal hyperparameter settings. So we can go ahead and run that cell just to store that function. And now we're ready to do our actual grid search CV. So we're using random forest classifier again, and we'll store that as RF. And this course isn't meant to get too in-depth into the individual algorithms, but essentially what random forest is a collection of decision trees. So take this decision tree. If we built 5 or 10 or 100 of those and then combined all of their predictions into one, that's what would be called a random forest. So each individual decision tree would be fit on some subset of data and some subset of features so that each decision tree was a little bit different. It's not critical that you understand it too in depth at this point. With that background, we just need to define our hyperparameter search region. So there are 2 hyperparameter settings that we want to tune. Number of estimators, so this means how many individual decision trees do we want to build within our random forest. And so for that, we're going to test 5, 50, and 100. And then secondly is max depth. And we talked about this a little bit in the slide above in a previous lesson, but this will just dictate how deep each of the individual decision trees go. So for that, we're going to test out 2, 10, 20, and none. And none will allow it to just grow the decision tree as deep as it needs to go until it hits some stopping criteria that's built in within the decision tree. So then what we need to do next is we'll just call the grid search CV method, and we have to pass in our model object, which is RF, our parameter dictionary, which is just parameters, and then the number of folds that we want. So in this case, we're doing 5-fold cross-validation. And then lastly, we'll just store that as CV. Now, if you've ever used scikit-learn before, you'll notice that their model training API is exactly the same no matter what type of algorithm you're using. So you'll store the object, and then you'll call .fit, passing in your features and your labels. Recall in the last lesson, scikit-learn wasn't too happy with the training labels because they're in a pandas column vector, and scikit-learn wants them to be an array. So we'll appease scikit-learn by converting it to an array using this values.ravel that we learned about last section. And then lastly, we can just call this print results function that I wrote above, and we'll just pass in that cross-validation object. Now, what this is going to do under the hood is it's going to take each parameter combination, so there's 3 levels of estimator and 4 levels of max depth, so that's 12 total combinations. And for each combination, it's running 5-fold cross-validation. So essentially, this is building 60 models under the hood. So again, 12 hyperparameter combinations with 5-fold cross-validation. There's 1 model for each combination. So that's 12 times 5 leads to 60 models being built. So let's go ahead and run this. You'll notice that we have 1 more warning. So this is a deprecation warning. And again, all this is telling us is that the default of a hyperparameter is going to be changing in a future version, but we don't need to worry about that too much. Now, it's telling us that the best hyperparameter values are max depth of 10 with 5 estimators. So we can look through the results and see that this setting generated an average accuracy of 82.8%. So that's only a little bit better than the roughly 82% that we saw with our baseline performance. Now, just looking through, the second and third best models here are this 82.6% accuracy with a max depth of 10 and 100 estimators, and 81.8% accuracy with no max depth and 100 estimators. So the only difference between these models and the model that gave us our baseline performance in the last lesson was that the baseline used the default values for number of estimators, which is 10, and the max depth, which is none. So interestingly, our best model has potentially a lower max depth and a lower number of estimators, but generates a little bit better performance, which suggests that maybe the default values were leading to a little bit of overfitting. But we don't really have enough information to concretely say that it was overfitting. Now, in the next lesson, we'll take these three models and evaluate them on the validation set to dig into these results a little bit deeper. Now that we've done some hyperparameter tuning, and we have a good idea of what the best hyperparameter combinations are, let's evaluate these models on some unseen data in the validation set. Now, the performance shouldn't deviate too much from the performance we saw with the cross-validation, because the performance metrics there were also on unseen data. But this will give us the opportunity to look at a couple additional performance metrics beyond just accuracy. So I do want to mention at this point that typically you'll test different algorithms as well. In this case, we're only using random forest classifier, just to keep things simpler. But usually we would have many different candidate models to choose from. In this lesson, we're going to take those three best performing models from the last lesson and really dig in to understand how they're performing. You'll notice that we're importing a couple additional metrics that we did not import last time. Now lastly, we're going to read in our data from the training and validation sets for this lesson, and then we'll read in our test set for the next lesson. So let's go ahead and run that cell. So here you'll see all the results we generated using grid search CV in the last section. So we're going to take the three best hyperparameter combinations and we're going to refit those models on the full training set. Why do we need to refit on the full training set? Remember that these models were originally fit only on 80% of the training data, because when we're doing five-fold cross-validation, in each loop, we're only using 80% of the data for training so that we can hold out that remaining 20% for testing. Now we want to evaluate this on the validation set, so let's allow our models to learn from the full training set instead of limiting it to only 80%. So we're going to start with the best hyperparameter combination that we found in the last lesson, and that was with number of estimators equal to 5 and max depth equal to 10. And then we'll store that as rf1, and then all we have to do is call rf1.fit and pass in our features and our labels. Now remember, we have to convert these labels from a pandas column vector into an array by calling .values.ravel. Now, remember that these hyperparameter settings will guide the way that this random forest classifier will fit to the full training set. Now, we want to do this for our top three models. So we'll just copy that code down. And our second best model had 100 estimators and also had max depth of 10. So let's assign that to rf2, and we'll change it down here for our .fit statement. And then our third best model had 100 estimators as well, with max depth of none. And then we'll assign that to rf3 and call rf3.fit. Now, once this cell is run, rf1, rf2, and rf3 will become fit models. So in other words, then we can take those and use it to make predictions on unseen data. So let's go ahead and run that. Now let's evaluate these fit models on the validation set. So the only examples these models have seen at this point are those in the training set. So this is the true test. It's the test of the model's ability to generalize to unseen data. If they're overfit or underfit, they'll fail here. Now remember from previous lessons that we'll be using accuracy, precision, and recall to evaluate these models to select the one that generalizes best to the validation set. So in order to evaluate these, we're going to use a for loop where we'll just cycle through our three models, rf1, rf2, and rf3. And then for each model, we'll call the .predict method. And then we just have to pass in our validation features, which is stored in val_features. So that will make predictions, and it will output an array of those features. And we'll just go ahead and store those as y_pred. So now that we have these predictions, now we want to generate some results metrics. So first, let's call accuracy score. And what you have to pass into accuracy score is first the actual labels So that's val underscore labels. That's what we read it in and stored it as. And then it wants the prediction, so y underscore pred. So we'll close that out, and then we're also rounding this to 3 decimal places just to make it a little bit cleaner. So next we want to generate the precision, so we can just copy this down because it uses the same syntax, and we just change it from accuracy score to precision score. And then lastly, we want to generate recall. So again, we can do the same thing, copy it right down, change that to recall score, and it'll store that as recall. And then all this last step is doing is it's just printing out the results. So it'll say for the model with a max depth of whatever that model's max depth is, and this number of estimators, here's the accuracy, the precision, and the recall. So we can go ahead and run that now. Now, you can see that the model that performed best in cross-validation actually didn't perform best on the validation set. Based on the hyperparameter settings, this first model is actually the most simple. It has the least amount of estimators, and it has a lower max depth. So it's possible that perhaps when we threw it the extra 20% of the training data, it just wasn't quite complex enough to learn the true patterns in the data, so it ended up underfitting. Again, we don't have quite enough information to say that concretely though. But we can see that the best model here is the second model. The accuracy is highest by a decent amount, the precision is much higher than the others, and the recall is second highest. Now, we're giving the edge to the second model here because the gain in precision is so large that it's worth the marginal loss in recall. But in many scenarios, it's much closer than that, and you'll have to use the context in which you're using this model to determine if precision or recall is more important to you. Now that we've evaluated all the models and we selected the best model as the one with a max depth of 10 and 100 estimators, in the next lesson, we're going to get one final unbiased view of how this model will perform on unseen data by evaluating it on the test set. Up to this point, you've done the following. You've explored the data to learn about feature relationships, the shape of the data, correlations to the target variable, and missing values. You've cleaned up the data to make the signal clear and easy for a model to pick up. You've split the data into train, validation, and test sets, and then you fit a basic model using cross-validation on the training set to set a baseline. You've explored 12 different hyperparameter combinations using grid search CV to figure out which hyperparameter settings would generate the best model. And you've refit the best few models on the full training set and evaluated them on the validation set to select the best model. And it all culminates with this final step. Now that we have the best model, we need to evaluate it on the test set to get a truly unbiased view of how it should perform moving forward. Now you might ask, why do we need to evaluate it on the test set when we already evaluated this model on unseen data with the validation set? And that's a great question. The validation set was created by just randomly distributing examples from the full data set. So if that validation set was slightly different, perhaps we would have chosen a different model. So by nature of the fact that it impacted what model was chosen as our final model, it's technically part of the model training process. So this final test set is purely for evaluation purposes, to see that it matches the performance that we've seen before, and to give us more confidence in the performance of the model moving forward. Now, we're basically just replicating the code that we saw in the last section. So we're using our best model, which was RF2, and that was already fit on the full training set. And then we're going to make predictions using our test features. And then we're storing that as ypred. And then just like we did in the last section, we're going to call accuracy score. And what that expects to see is your actual labels and then your predictions. And then again, we're rounding this to 3 decimal places. And then we can just copy this down for precision. And we'll just change it from accuracy score to precision. And then once more down for recall, and we'll just change it from accuracy score to recall. And it's going to print out the max depth and the number of estimators for this specific model that we're running. So let's go ahead and run this. And I'd just like to highlight that if you're running this along with me, or even if I went back and ran this whole notebook again, we might get slightly different results here. We'll even have slightly different models. Because when we're creating our training, test, and validation sets, that's randomly distributing those examples, so you at home will have different training, test, and validation sets than I will. And even if we have the exact same data and we're using the exact same hyperparameters, there's some randomness within the model in terms of how it builds, so we can have different results even if everything else is exactly the same. Looking at these performance metrics, and circling all the way back to Grid Search CV, the model with these hyperparameter settings had 82.6% accuracy for Grid Search CV, it had 83.2% accuracy on the validation set, and then 79.8% accuracy on this test set. So this just highlights how the performance of a given model can vary based on the data you give it. This is the exact same model being fed two data sets that were just randomly sampled from our full data set. So in theory, we would expect these two data sets, the validation set and the test set, to look very similar. And they probably do, but they're just different enough for a model to accurately predict survival in 83.2% of the passengers in one of them and 79.8% in the other. All this is to say that testing your model on unseen data and properly accounting for error bars and variability in those performance metrics is absolutely critical. So great job. Now you've gone all the way through an entire machine learning pipeline to build a robust model that successfully generalizes to unseen examples. Now you're ready to take this foundation of skills you've built up and use it to solve complex problems by delivering powerful machine learning solutions. Congratulations! You now have the tools to go from messy data to concise, accurate predictions. This foundation of knowledge and skills that you've built sets you up to build models in a variety of industries on various types of problems with any kind of algorithm. This is an incredibly powerful tool. But don't stop here. We only touched on the foundations. Use this as a building block to continue learning and building your own powerful models. Here are a few next steps that you could take. Now that you have the foundation to build on top of, explore a variety of different algorithms beyond random forest in my other course, Applied Machine Learning Algorithms. This machine learning and AI foundations, classification modeling. Lastly, one of the best machine learning resources out there is called Fast.ai. And this was started by Jeremy Howard, formerly the president of Kaggle. They have blog posts and really specialize in making deep learning as practical and tangible as possible. But above all, don't stop here. There's no substitute for actually getting your hands dirty and doing this work yourself. That hands-on experience will further hone your technique, skills, and intuition.